In the vast, endless expanse of space, there are stars that seem to challenge the very laws of nature. Among them is UY Scuti, a star so gigantic that it makes our Sun look like a mere speck of dust. Located over 9,500 light-years away, UY Scuti is a true giant, with a radius so vast it could encompass the orbit of Jupiter with room to spare. But what does it mean to witness a star of such magnitude? How does a star grow to such an unimaginable size, and what role does it play in the grand scale of the universe's life cycle? In this video, we're diving deep into the story of UY Scuti, a star that has captured the attention of astronomers and stargazers alike. From its origins to its explosive future, UY Scuti is a shining example of the extremes of the cosmos. Join us as we explore this cosmic behemoth, uncovering the science, the phenomena, and the mysteries behind one of the largest stars we've ever discovered. UY Scuti resides in the constellation Scutum, a lesser-known region of the night sky that doesn't grab headlines like Orion or Ursa Major. But within this relatively quiet neighborhood of stars sits one of the most astonishing celestial bodies known to science. Roughly 9,500 light-years away, UY Scuti is classified as a red supergiant, or more precisely, a pulsating variable star. That classification alone tells us a great deal. It's nearing the end of its life, it's bloated in size, and it's unstable. And yet, in its instability, it has become something awe-inspiring. This star doesn't merely exist, it dominates. With a radius estimated to be around 1,700 times that of our Sun, UY Scuti's circumference is so massive that if it were hollow, nearly 5 billion suns could fit inside of it. The numbers associated with UY Scuti break the mind. The diameter of this star is approximately 2.4 billion kilometers, or about 1.5 billion miles. And although its mass is not the greatest, perhaps only 30 times that of the Sun, its volume is what sets it apart. The sheer bulk of this star defies conventional understanding. But to truly appreciate UY Scuti, one must dive deeper into the science, into the origin and life cycle of massive stars, and into the methods we use to measure these distant objects. UY Scuti is not simply big, it is a lens through which we study the ultimate fates of stars, the nature of matter, and the complexity of stellar evolution. Let's start with how we even know UY Scuti exists in the first place. Located near the center of our Milky Way galaxy, UY Scuti was first catalogued in 1860 by German astronomers at the Bonn Observatory. At that time, it was simply another red giant in the starry sky, not yet recognized for the colossus it truly is. For more than a century, it remained relatively obscure. Only with the advent of advanced astronomical techniques, infrared observations, precise parallax measurements, and spectroscopic analysis, did the full scale of UY Scuti become apparent. It was during a survey conducted at the European Southern Observatory in the early 2010s that the full, jaw-dropping extent of UY Scuti's radius was finally realized. Now, when we say that a star has a radius, we're speaking in relative, often dynamic terms, especially in the case of variable stars like UY Scuti. Unlike solid planets, stars are made of plasma, a highly energetic soup of subatomic particles. This means their edges are not fixed. They're not bordered by rock or crust, but by gradients of light and heat, pressure and density. In the case of red supergiants, their outer layers are incredibly diffuse, puffed up by internal convection and radiative forces. As such, the radius of a star like UY Scuti is often measured as the point where its opacity falls below a certain threshold, where light can escape its outer envelope. These outer layers are so tenuous that if a spacecraft were flying through them, it might not even detect much resistance, like soaring through a barely there fog that stretches across millions of kilometers. Yet this fog is hot, unstable, and ever-changing. UY Scuti pulsates over time, expanding and contracting as it burns the last remnants of its hydrogen fuel and begins the fusion of heavier elements. Its size, then, is not static. The radius of UY Scuti may vary by hundreds of millions of kilometers over cycles that last months. This variability complicates efforts to nail down a precise measurement, but even on its smallest scale, UY Scuti would still be among the largest known stars in the observable universe. The term red supergiant, is itself a loaded label. It signals an advanced stage in stellar evolution, a kind of cosmic swan song. Stars like UY Scuti have evolved from main sequence giants that once burned hydrogen in their cores efficiently. Over millions of years, the hydrogen ran out, the core contracted, and temperatures rose, igniting shells of helium and heavier elements. The outer layers, freed from the gravitational grip of the dense core, balloon outward, producing the immense size we observe. This stage doesn't last long. In cosmic terms, the red supergiant phase is a brief, violent chapter at the end of a long stellar life. UY Scuti is living on borrowed time. Millions, maybe hundreds of thousands of years from now, it will collapse into either a neutron star or a black hole, likely after a spectacular supernova explosion. That explosion could be visible from Earth, even at a distance of nearly 10,000 light-years. It may even temporarily outshine the moon in our sky. But until that day comes, UY Scuti remains a quiet titan in the darkness. Its light travels across eons, reaching Earth after traversing nearly a third of the Milky Way's disk. That light is a message in a bottle from the past, from a star so large that if Earth were placed on its surface, it would take years to orbit all the way around. The atmosphere of UY Scuti is a violent place. Stellar winds sweep across its bloated surface at speeds of hundreds of kilometers per second, ejecting material into space in great arcs and plumes. These outbursts of stellar matter form a dusty, glowing nebula around the star, a kind of shroud that both conceals and reveals its nature. Infrared telescopes like those aboard the Spitzer Space Telescope and the Very Large Telescope in Chile have been essential in penetrating this dust to study the true nature of the giant within. What scientists have found is a star struggling against gravity, heat, and time. The fusion reactions in its core are unstable, causing seismic waves to ripple through its outer layers, resulting in cyclic dimming and brightening. These pulsations give astronomers valuable data about its internal structure, data that can be analyzed through the science of astroseismology, which is, in essence, the study of star quakes. And UY Scuti is not alone in the category of hypergiants, although it reigns near the top. Other contenders for the largest star include VY Canis Majoris, Betelgeuse, and RW Cephei. Some of these have larger radii under specific observational models or during certain phases, but none consistently rival UY Scuti's volume across multiple measuring techniques. Even more intriguing is the question of how UY Scuti formed. Stars this large don't just appear, they're born from enormous molecular clouds containing hundreds or thousands of solar masses worth of gas and dust. It's likely that UY Scuti was born in a stellar nursery rich in material, undergoing rapid fusion early in life that catapulted it into its massive state. Its life has likely been filled with drama, constant mass loss, possibly binary interactions with unseen stellar companions, and a continuous struggle to maintain equilibrium between gravitational collapse and nuclear fusion. That equilibrium is delicate. One misstep, one shift in internal balance, and the star's life ends in cataclysm. But before that finale, we are left with this awe-inspiring entity, a star that pushes our understanding of size, physics, and the structure of the universe itself. UY Scuti is not just a star. It is a benchmark for what stars can become. It teaches us about the limits of size, the instability of advanced stellar evolution, and the interplay between light, matter, and energy on an unfathomable scale. To better grasp the scale of UY Scuti, let's step away from abstract numbers and dive into a thought experiment, one that turns imagination into measurement. If a commercial passenger jet were to fly around the surface of UY Scuti at 900 km per hour, about 560 miles per hour, it would take over 1,100 years to make a single loop around the star's circumference. To fly around the Sun, by comparison, would take just a few months. This staggering disparity helps put into perspective just how immense UY Scuti truly is. When humans speak of size, we often reference mountains, continents, or even our planet. But UY Scuti operates on a scale so far beyond any terrestrial comparison that even the vastness of our solar system seems almost quaint in contrast. Light itself, the fastest thing in the universe, would take approximately 7 hours to travel from one side of UY Scuti to the other, assuming its radius to be 1,700 times that of the sun. Light crosses Earth in a fraction of a second, the Moon in just over a second, and even the Sun in about 4.6 seconds. But UY Scuti? Hours. And this is from light. Think about that. A human being walking across the diameter of UY Scuti would need billions of years, longer than the current age of our species. It's not just big, it's cosmically enormous. Yet UY Scuti's story is not merely one of size. It is a tale of physics under stress. Its enormous radius is matched by an intricate balance of forces working in concert, struggling for dominance. On one side is gravity, an ever-present, inward-pulling force trying to compress the star into a denser, more compact form. On the other side is radiation pressure, the result of immense nuclear fusion reactions occurring at the star's core. These reactions generate not just light and heat, but also a kind of internal push that counteracts gravity. The result is a kind of stellar stalemate, a precarious balance that allows the star to retain its shape and size, for now. As UY Scuti exhausts its remaining nuclear fuel, this balance becomes harder to maintain. The fusion process that keeps it inflated is unsustainable over the long term. Fusion, after all, is a chain of events. Hydrogen fuses into helium. Helium into carbon. Carbon into heavier elements like neon, oxygen, and silicon. Each step generates less energy than the last, and each step requires higher and higher core temperatures. When iron is eventually formed, if the star gets that far, the process stops. Iron cannot be fused into heavier elements without consuming energy, rather than releasing it. At that point, gravity wins. The core collapses. The outer layers are blown apart in a supernova. The end. UY Scuti, though still burning, is likely well into this sequence. It is considered a highly evolved star, meaning it has already passed through several fusion stages. It is shedding mass at a prodigious rate. Its outer envelope, composed of gas and dust, is being expelled into space, forming a complex and beautiful circumstellar environment that astronomers have only just begun to map. Observing these expelled materials gives us a glimpse into the future, not just of UY Scuti, but of many massive stars. These nebulae act like fingerprints, telling scientists about the composition, temperature, pressure, and movement of materials long after they've left the star's surface. In a way, the space around UY Scuti is alive with history, a fluid archive of the star's evolutionary path. Another fascinating aspect of UY Scuti is its variability. It is classified as a semi-regular variable star, meaning that its brightness shifts in somewhat predictable patterns over time. These shifts are due to pulsations in its outer layers, swells and contractions that occur as a result of the energy dynamics deep within the star. Each pulse can cause the star to dim or brighten over a period of hundreds of days. These fluctuations offer vital clues about the star's internal structure, just as earthquakes reveal the interior layers of Earth. In astronomy, this study is called astroseismology, the science of stellar oscillations. And in UY Scuti, these oscillations are particularly dramatic, indicating that the interior is as unstable as the star's outer appearance would suggest. But how exactly do astronomers study such a distant and gigantic object? UY Scuti is not close to Earth. It lies nearly 9,500 light-years away in a region of the Milky Way that is dense with interstellar dust, making direct observation difficult in visible light. That's where infrared astronomy becomes crucial. Infrared light penetrates dust much more effectively than visible light, allowing telescopes to capture detailed images and spectra of UY Scuti's structure. One of the key tools used in this effort is the Very Large Telescope, VLT, in Chile, operated by the European Southern Observatory. With adaptive optics and high-resolution infrared imaging, the VLT has helped refine measurements of UY Scuti's radius and luminosity. These observations must be pieced together carefully, because the exact size of UY Scuti remains a subject of scientific debate. Some models suggest a slightly smaller radius than the widely cited 1,700 solar radii, depending on assumptions about temperature, distance, and opacity. However, Even conservative estimates place it firmly among the largest stars ever observed. There's also the question of mass loss, a process that is rapidly reshaping UY Scuti's destiny. Stars like UY Scuti lose mass at an astounding rate, potentially millions of times more than our Sun does through the solar wind. These mass loss rates are important because they affect how a star evolves. They influence how quickly it burns through its fuel, what kind of supernova it might become, and what will be left afterward: a neutron star, a black hole, or nothing at all. UY Scuti's massive winds and ejecta suggest that it may already be well along this pathway. The star may be blowing off its outer layers faster than it can sustain them, essentially peeling itself apart from the outside in. This process creates a cocoon of gas and dust that both shields the star and complicates our efforts to study it. Yet within that shroud lies some of the most fascinating stellar physics in the observable universe. In a sense, UY Scuti is both an individual and a prototype. It stands alone as a celestial record holder, but it also represents a category of extreme stellar evolution. By studying it, we learn about the fate of other supergiants. We gain insights into how elements are forged in the last moments of stellar life, how supernovae seed the cosmos with heavy metals, and how black holes might form in the remnants of collapsed cores. The implications ripple outward. Without stars like UY Scuti, the universe would be a barren place. These massive stars are the engines of cosmic alchemy. They create the calcium in your bones, the oxygen in your lungs, the iron in your blood. Every heavy element in your body was forged in the heart of a star, many of them in stars not unlike UY Scuti. Its story, then, is also our story. The atoms that make up your body were once light years away, perhaps part of a giant like UY Scuti, long before they were incorporated into Earth, and eventually into you. As we peer deeper into the cosmos with next-generation telescopes like the James Webb Space Telescope, we may find even more enormous stars, perhaps even ones that rival or exceed UY Scuti in volume. But for now, UY Scuti remains a monument to the maximum of what nature can achieve in stellar terms. It's a reminder that the universe is stranger, grander, and more immense than we often allow ourselves to imagine. It challenges astronomers to improve their tools. It invites thinkers to question the boundaries of size and scale. And it humbles every human being who learns of its existence. For how can one truly grasp a star whose diameter could stretch from the Sun to Jupiter and beyond? How can we, finite creatures bound to a small blue planet, even begin to internalize the significance of something so vast, so ancient, so alien? It's important to understand that UY Scuti's place in astronomical history is not merely the result of one discovery or one telescope session. Its legacy has been built over decades of observational refinement. The earliest documented measurements of this star date back to the 19th century, when astronomers catalogued it as a variable star, noting subtle shifts in brightness without having any idea of its true size. Back then, with no modern instruments, and no way to measure parallax accurately over such distances, the concept of a star spanning more than 1,000 times the radius of the Sun was unimaginable. As technology advanced, particularly in the 20th and 21st centuries, the layers of mystery surrounding UY Scuti began to peel away. Spectroscopic measurements allowed scientists to understand its composition and temperature. Infrared data helped bypass the dense clouds of interstellar dust that obscure visible light. And long-term photometric observations revealed a pattern of pulsations, confirming its classification as a pulsating red supergiant. Each of these data points built a fuller picture, slowly assembling the identity of a star so massive that even modern astrophysics struggles to contain it in formulas. What makes UY Scuti especially intriguing is how it redefines our sense of what's possible in the universe. It compels a re-examination of stellar models. Standard theories of stellar evolution tell us that stars this large shouldn't exist for long. Their lifespans are astronomically brief, mere millions of years, compared to smaller stars like our Sun, which burns steadily for billions. UY Scuti, then, is in a race against time, a race it is destined to lose in spectacular fashion. That loss, however, is the universe's gain, because the death of a star like UY Scuti will release a cascade of elements that enrich surrounding space. The mechanism of that death is worth examining closely. When UY Scuti's core can no longer sustain nuclear fusion, it will begin to collapse under the immense pressure of its own gravity. This process happens so quickly and so violently that the outer layers of the star are expelled at incredible speeds. The energy released in such a collapse is almost incomprehensible. A single supernova can outshine an entire galaxy for weeks, releasing more energy in that brief moment than the Sun will in its entire 10 billion year life. Whether UY Scuti will end in a Type II supernova or collapse directly into a black hole remains uncertain. Both outcomes are possible. Some models suggest that if the star's mass loss continues at a rapid pace, it might shed enough material to reduce its core below the threshold necessary for direct collapse. In that case, it could leave behind a neutron star, a city-sized sphere of incredibly dense matter. If not, a black hole will likely form, an object so dense that not even light can escape its gravity. Either way, what remains of UY Scuti will be fundamentally transformed. This process, while violent and final, is not the end of UY Scuti's story. The materials cast off during its life and explosive death will drift through the interstellar medium, mixing with gas and dust to form new stars, planets, and possibly even life-bearing systems. This cycle of stellar birth and death is one of the most beautiful and fundamental truths in astrophysics. UY Scuti is not just a dying star, it is a precursor to the next generation of the cosmos. The chemical fingerprints it leaves behind, carbon, oxygen, magnesium, iron, will linger for billions of years. If a planet forms from this enriched matter, and life eventually arises there, those future beings will owe their existence in part to a star they never knew, one that burned out long before their world was born. That is the legacy of stars like UY Scuti. They are not just markers in the sky or objects of curiosity. They are the architects of matter, the seeders of possibility, and the silent authors of the atoms that compose everything we are. When thinking about UY Scuti, it's essential to grasp the interplay of heat, pressure, magnetism, and time. Its surface temperature, estimated to be around 3,365 Kelvin, is cooler than that of the Sun, which has a surface temperature of about 5,778 Kelvin. That might seem counterintuitive. How can a star so massive be cooler than our Sun? The answer lies in the nature of red supergiants. As these stars expand, their energy spreads over a much larger area, lowering their surface temperature while increasing their total output. Despite being cooler, UY Scuti is vastly more luminous, radiating nearly 340,000 times more energy than the Sun. This immense energy output causes powerful stellar winds that carry particles away from the star at high velocities. Over time, these winds strip UY Scuti of its mass, creating a halo of ionized gas that stretches far into space. This halo can be detected by radio telescopes and used to study the star's mass loss rate, giving astronomers clues about how much time UY Scuti has left. Observations suggest that it's nearing the final phases of its life, though in cosmic terms that might still mean hundreds of thousands of years. Studying UY Scuti also helps astronomers refine their understanding of the Hertzsprung-Russell diagram, a key tool in stellar astronomy. This diagram plots stars according to their brightness and temperature, revealing patterns that correspond to different stages of stellar evolution. UY Scuti occupies a position at the far end of the red supergiant branch, a place few stars reach and fewer still survive for long. It challenges the assumptions baked into the diagram and forces astronomers to consider outliers, stars so vast and unstable that they break the rules of more familiar stellar models. Another tool used in understanding UY Scuti is interferometry, a technique that combines light from multiple telescopes to simulate a much larger one. This method allows astronomers to resolve features on the surfaces of distant stars, even those thousands of light years away. Using interferometry, scientists have detected asymmetries and hotspots on UY Scuti's surface, evidence of massive convective cells that churn beneath the photosphere. These convection currents transport heat from the star's interior to its surface, and in stars as large as UY Scuti, these cells can be so large that they cover a significant portion of the entire star's visible disk. These features are dynamic, shifting and changing over time, contributing to the star's semi-regular variability. The pulsations also produce shock waves that propagate through the star's outer layers, compressing and heating the gas in complex ways. These shocks can trigger bursts of mass ejection or change the star's brightness abruptly. Monitoring these fluctuations over years helps astronomers build more accurate models of stellar atmospheres and dynamics, which are essential for predicting the star's eventual collapse. UY Scuti stands as a symbol of extremity. In a cosmos filled with billions of stars, it is one of the largest known by radius. Its sheer scale inspires humility. If Earth were a marble, and the Sun a basketball, then UY Scuti would be a balloon the size of a sports stadium. Trying to hold that scale in your mind is nearly impossible. And that's the point. UY Scuti breaks the mind open, stretches the imagination, and invites questions that lead us deeper into the mysteries of existence. Its vastness is not just a matter of raw measurement, it is an invitation to reconsider everything we think we know about stellar physics. For UY Scuti, the definition of size becomes almost abstract. When we say it has a radius approximately 1,700 times that of the Sun, it's easy to hear the number and move on. But what does that really mean? It means that if UY Scuti were to replace the Sun at the center of our solar system, its outer layers would extend beyond the orbit of Jupiter, possibly even encroaching on Saturn's. All of the inner planets, Mercury, Venus, Earth, Mars, and much of the asteroid belt would be swallowed whole. That's not just large, that's incomprehensibly colossal. Yet despite this enormity, UY Scuti's mass is estimated to be only 7 to 10 times that of the Sun. This discrepancy between size and mass is crucial in understanding how such a star functions. Its mass is not spread uniformly across its volume. Rather, UY Scuti is mostly made of diffuse, low-density gas. Its outer envelope is extended and tenuous, barely held together by gravity. This is a characteristic of red supergiants in their final stages of life. The core is small, dense, and rapidly fusing elements, while the outer layers puff out to form an enormous shell of cooler plasma. These layers are so fragile that even minor instabilities can eject huge quantities of material into space. We have observed this in action. Astronomers have seen evidence of gigantic mass loss events in UY Scuti's history. Clouds of gas and dust have been detected in its vicinity, likely expelled in great convulsions that shook the star to its core. These ejections don't just contribute to the star's eventual demise, they are its legacy. They enrich the surrounding interstellar medium with heavy elements that would never have formed in the early universe. Everything from the calcium in our bones to the iron in our blood owes its existence to the supernovae of massive stars like UY Scuti. As it sheds mass and nears its final act, UY Scuti provides a living laboratory for scientists who study stellar evolution. By observing it in real time, we get a rare glimpse into what happens when the balance of pressure and gravity begins to falter. In its interior, nuclear fusion is transitioning from burning lighter elements like hydrogen and helium to heavier ones such as carbon, oxygen, and eventually silicon and iron. Each of these fusion processes releases less energy than the last, and once iron builds up in the core, the star reaches a critical threshold. Iron cannot be fused to produce energy, it only absorbs it. At that point, the outward pressure that has held the star aloft for millions of years collapses, and gravity takes over in an instant. The core implodes, triggering a cascade of reactions that produce neutrinos, tiny, nearly massless particles that escape almost instantly. These neutrinos play a surprising role. They deposit energy into the surrounding stellar material, helping blow it apart in a cataclysmic explosion. This is the moment of supernova, a flash so bright it could be seen from galaxies away. If UY Scuti were to go supernova within our lifetime, though it's incredibly unlikely given the vast timescales, it could become the brightest object in Earth's sky for weeks, even visible during daylight. It would be a cosmic fireworks show, a finale for a star that lived fast and died hard. But even after that death, UY Scuti's story wouldn't truly end. The remnants of the explosion would form a nebula, a vast cloud of gas and dust spreading outward through the galaxy. The shockwaves would trigger the birth of new stars in nearby molecular clouds. This is the poetic irony of stellar death. It leads directly to new life. From one dying red supergiant, dozens or even hundreds of new suns might be born, each carrying within them trace elements forged in UY Scuti's heart. This cycle of creation and destruction has continued for billions of years and will continue for billions more. Our own sun was born from the ashes of stars like UY Scuti. Somewhere in its chemical fingerprint, we can find isotopes that tell the story of ancient supernovae. Our Earth, our bodies, our breath, it all traces back to stars that lived and died long before our solar system existed. So when we gaze upon UY Scuti, we are not just looking at a distant sun, we are looking at one of our ancestors. There's something deeply humbling about this realization. The cosmos is not separate from us. We are made of the same stuff as the stars. And yet, despite our shared material heritage, we are radically different in scale and nature. UY Scuti is nearly 1,000 times wider than the sun, and yet we, tiny creatures on a small rock orbiting that modest star, have developed tools and minds capable of comprehending, at least partially, the grandeur of such a behemoth. The story of how we came to know about UY Scuti is a triumph of human ingenuity. Early observations were conducted at the Bonn Observatory in Germany, where it was first catalogued in 1860. Back then, it was just another faint point of light in the sky, designated BD, 12°50'55. It wasn't until more recent surveys, particularly the use of interferometry and data from the European Southern Observatory, that astronomers began to grasp its true size. The usage of very long baseline interferometry, VLBI, and adaptive optics allowed for more precise distance measurements and angular diameter calculations. These techniques revealed a star so vast, so enveloping, that it stretched the limits of what we thought stars could be. Even with these observations, UY Scuti's precise size remains a subject of debate. The margin of error is considerable because of the difficulty in pinning down its exact distance and the fluctuating nature of its atmosphere. Estimates range from around 1,400 to over 1,700 solar radii, depending on how you define its boundary. Some researchers argue that its outer envelope is so diffuse that it's hard to say exactly where the star ends and interstellar space begins. Regardless, even conservative estimates place UY Scuti among the largest known stars by radius, if not the absolute largest. Comparisons often arise with other colossal stars like VY Canis Majoris, Betelgeuse, and RW Cephei. Each has its own claim to the title of largest, depending on whether you measure by radius, volume, or mass. But UY Scuti remains an emblem of the extreme, a benchmark against which all other giants are measured. Its vast girth and relatively short lifespan encapsulate the tension at the heart of stellar physics. The bigger a star is, the more quickly it burns through its fuel. In a way, UY Scuti is like a cosmic flame that blazes brighter and larger than almost any other, but at the cost of longevity. The broader scientific community continues to monitor UY Scuti not just out of curiosity, but because it provides data crucial to refining our models of stellar evolution. Understanding its pulsations helps with astroseismology, the study of stellar oscillations, which can reveal details about the star's internal structure. Studying its mass loss mechanisms informs research into galactic chemical enrichment. Tracking its brightness variations improves techniques in variable star observation. Every piece of information gleaned from UY Scuti is a puzzle piece in the grand mosaic of our understanding of the universe. Because UY Scuti lies at the very limits of what a star can be, it challenges every equation and model designed to explain stellar behavior. It is not simply an anomaly. It is an edge case that forces astrophysicists to stretch their assumptions and ask uncomfortable questions. Can a star grow any larger and still remain bound by gravity? Can our current models accurately simulate the complex interplay between radiation pressure, gravity, and convective currents at such vast scales? And what does UY Scuti's existence imply for the ultimate fate of supermassive stars in general? Its pulsating nature offers yet another window into its mysterious workings. Like many red supergiants, UY Scuti is a variable star, specifically a semi-regular variable. This means its brightness fluctuates over time, not in a random way, but in somewhat predictable patterns. These pulsations are not just superficial dimming and brightening, they are surface echoes of deep internal processes. Each pulse can change the diameter of the star by hundreds of solar radii, subtly inflating and contracting its already monstrous frame. These cycles occur over spans of months and are the result of complex interactions between gravity and pressure deep within its interior. These fluctuations help scientists estimate the star's internal structure, even when direct observation is impossible. Even more remarkably, these brightness changes can give us indirect insight into what is happening in UY Scuti's convective zones. The convection in red supergiants is unlike that in stars like our Sun. Because of their size and relatively low surface gravity, the convective cells in stars like UY Scuti are absolutely massive, larger than entire planets. These convective zones churn slowly but powerfully, moving hot plasma from the inner layers to the surface and releasing energy in the form of light and stellar wind. This process leads to surface irregularities, dark patches, and local temperature changes that can be detected by sensitive photometric instruments. These enormous convective cells also play a role in how UY Scuti loses mass. The material from its outer layers is so loosely bound that when these upwellings reach the surface, they can hurl gas into space with only minimal resistance. Over time, this contributes to a slow but steady erosion of the star's mass, creating a massive stellar wind that forms a halo around the star and adds to the interstellar dust. Some models estimate that UY Scuti loses as much as 1 Earth mass worth of material every year. In stellar terms, this may seem small, but over the star's final million years, it adds up to a significant portion of its envelope. It's worth pausing here to consider the visual appearance of UY Scuti. If we could fly a spaceship into close orbit, keeping in mind the overwhelming radiation and stellar winds that would make such a feat impossible, we would see something truly surreal. Its surface would not be a uniform glowing sphere but a shifting, writhing expanse of reds and oranges, interspersed with dark blotches where cooler gases momentarily dominate. The atmosphere would be thick with expelled material, gas, dust, and perhaps even molecules forming in the cooler regions. It would look more like a foggy, boiling sea of fire than anything we traditionally associate with stars. And while it glows in visible light, much of its energy is emitted in the infrared spectrum, due to the relatively low surface temperature of around 3000 Kelvin. Observations in the infrared are crucial in studying such stars, as they penetrate the dust that often surrounds these titanic bodies. Instruments like those on the Very Large Telescope and the Herschel Space Observatory have captured images of UY Scuti's extended envelope, revealing details about the outflows and shock fronts created as it sheds its outer layers. These data help scientists estimate the age of the surrounding gas clouds and track the movement of materials through interstellar space. Each filament of gas around UY Scuti tells a story, a moment when part of the star was violently expelled and cast into the void. Now, in understanding the full life cycle of UY Scuti, it's essential to recognize its place in the Hertzsprung-Russell diagram, the tool astronomers use to classify stars based on their luminosity and temperature. UY Scuti lies far in the upper right quadrant of this chart, firmly in the domain of red supergiants. Its immense size is accompanied by high luminosity, despite its relatively cool surface. This combination is rare and short-lived. Stars do not remain in the red supergiant phase for long, perhaps 1 million years at most, compared to the billions of years spent on the main sequence. In cosmic terms, it is a blink of an eye, the swan song before the final curtain. This leads us to speculate about the future of UY Scuti. When the final layers of fusion run their course, and the core becomes dominated by inert iron, collapse will be inevitable. Depending on the exact mass of the core at that moment, the collapse may result in either a neutron star or a black hole. If UY Scuti's core is above the Tolman, Oppenheimer, Volkoff limit, the maximum mass a neutron star can support, it will collapse beyond the point of no return and form a black hole, a region of space from which nothing, not even light, can escape. This transformation would be accompanied by one of the most violent events in the universe, a supernova explosion. Such an explosion would be devastating in its immediate vicinity, unleashing shockwaves that could compress nearby interstellar clouds and trigger new rounds of star formation. But given UY Scuti's distance, about 9,500 light-years from Earth, we would not be directly affected by the blast. We would, however, be treated to a celestial show unlike any in recorded human history. For weeks, the supernova might outshine all other stars in the sky, becoming visible even during daylight. Telescopes around the world and in orbit would turn their gaze toward the spectacle, gathering data that could redefine our understanding of supernova mechanics. But until that day arrives, likely millions of years in the future, UY Scuti continues its slow dance at the edge of existence. It pulsates, breathes, and sheds its skin, a cosmic leviathan biding its time. It serves as a reminder of how large, how complex, and how beautiful the universe can be. It also illustrates the duality of scale, that something can be so vast and yet so fragile, so luminous and yet so ephemeral. Its discovery and study are not just the product of human curiosity, they are a testament to our capacity for wonder. From a speck of light catalogued in the 19th century to one of the most extraordinary known stars in our galaxy, UY Scuti's journey is also our journey. It is the story of our expanding awareness, our ever-deepening gaze into the abyss, and our persistent search for meaning in a universe that often seems indifferent to our presence. But perhaps the most poetic aspect of UY Scuti is what it leaves behind, not just in the physical sense, with the gases and elements that will one day become part of other stars and planets, but in the mental space it opens within us. When we learn about UY Scuti, we are forced to stretch our imaginations to scales we rarely consider. We are confronted with dimensions and forces far beyond our daily lives. And in doing so, we gain perspective, not just on the cosmos, but on ourselves. For in contemplating a star so vast it could swallow planets whole, we also confront the fragility and preciousness of our own existence. We realize how rare it is that, in a universe of titanic explosions and cosmic collisions, there exists a small, stable world where life can not only survive but ponder the stars. UY Scuti, then, is not just a subject of study. It is a mirror, reflecting back to us both the grandeur of the universe and the miracle of consciousness. And still, there remains so much more to uncover about UY Scuti, its internal composition, its precise mass, its full evolutionary trajectory, and its eventual fate. For all the observations we've made, the star remains, in many ways, an enigma cloaked in its own luminous shroud. It beckons astronomers with questions that seem both incredibly specific and overwhelmingly cosmic. How do elements behave in a star where gravity and pressure create near-alien conditions? How do convection and radiation balance in such a gargantuan envelope? What mechanisms define the boundary between stability and collapse in a body so massive and tenuous? When we consider UY Scuti's physical properties, we come up against the limitations of even our most advanced instruments. Measuring something nearly 1 billion miles across that lies thousands of light-years away is not a simple task. The star's estimated radius, over 1,700 times that of the Sun, is not an absolute figure but one that depends on how we define the star's outer boundary. This is because the outer layers of a red supergiant like UY Scuti are not clearly defined. They are made of partially transparent gas that gradually fades into the interstellar medium, and this ambiguity creates substantial measurement uncertainty. To estimate its size, scientists rely on a combination of methods: interferometry to directly image the star's disk, spectral analysis to measure temperature and composition, and light curve data to map pulsations. Yet these measurements must be corrected for interstellar dust, variations in brightness, and other environmental factors. The value we assign to UY Scuti's radius today may well change tomorrow as observational techniques improve. But whether it turns out to be the largest star, or merely one of the largest, is almost secondary. What matters is that it stands as an extreme case, one that helps define the upper limits of stellar existence. Its distance from Earth, roughly 9,500 light-years, places it in the constellation Scutum, near the star-rich plain of the Milky Way. This location makes it difficult to observe in optical light because of the dense clouds of interstellar dust that lie between us and the star. Fortunately, infrared observations can penetrate this obscuration, allowing us to peer into the heart of the galaxy and view objects like UY Scuti with surprising clarity. The use of infrared astronomy has revolutionized our understanding of red supergiants, revealing the thermal radiation they emit and the dust shells they produce. It's through these wavelengths that we gain our clearest view of UY Scuti's size, shape, and mass loss behavior. Now, imagine trying to simulate such a star on a computer. The sheer scale of it defies easy modeling. Computational astrophysics has come a long way, but modeling the entire volume of UY Scuti in full 3D detail, including magnetohydrodynamics, nuclear fusion, radiative transport, and fluid dynamics, remains a challenge of staggering complexity. Scientists often must settle for simplified models, 1D or 2D simulations that use approximations for convection, opacity, and core fusion. These models give us broad insights but often miss the chaotic surface activity or asymmetric mass ejections that real stars like UY Scuti undergo. That chaotic nature is evident in the star's surroundings. The material UY Scuti has ejected into space doesn't disperse uniformly. It forms arcs, clumps, and streamers, structures sculpted by magnetic fields, stellar winds, and gravitational perturbations. These features are not just beautiful. They are repositories of information. Each arc of gas carries signatures of the star's inner chemistry: carbon, nitrogen, oxygen, and other heavier elements forged through nuclear fusion. These elements will one day enrich the interstellar medium, becoming part of new star systems. In this way, UY Scuti plays a role in cosmic recycling, a process that spans billions of years and links the death of old stars to the birth of new ones. There's also a mystery in how red supergiants like UY Scuti evolve in their final phases. Do they shed their outer layers gradually, or do they experience sudden episodes of extreme mass loss? Do they enter brief phases of hyperluminosity, ejecting much of their mass in the span of centuries? Some theories suggest that red supergiants can undergo luminous blue variable, LBV, like phases, where instability drives bursts of radiation and matter into space. Others propose that binary interactions, if UY Scuti has a hidden companion, could strip mass away via gravitational siphoning, altering the star's evolution significantly. So far, there is no confirmed companion to UY Scuti, but the absence of evidence is not evidence of absence. Given its massive envelope and the density of stars in its region of the galaxy, it is entirely plausible that UY Scuti could have a nearby stellar neighbor. A binary system involving a red supergiant could produce fascinating phenomena, accretion disks, periodic brightening, and even explosive novae under the right conditions. Discovering such a companion would open entirely new avenues of inquiry and potentially rewrite our understanding of UY Scuti's mass loss and evolution. One particularly intriguing aspect of UY Scuti and similar stars is their role as cosmic laboratories. The conditions inside such massive stars cannot be recreated on Earth, not even in the most powerful particle accelerators. The extreme temperatures and pressures in UY Scuti's core make it a natural fusion reactor, synthesizing elements through pathways that differ depending on core temperature and composition. These include the carbon-nitrogen-oxygen (CNO) cycle, which dominates in stars heavier than the Sun. By studying the byproducts of these processes, visible in the star's spectral lines, we can reverse engineer the fusion reactions happening deep within. And yet, all this complexity leads to a stark, singular fate. At the end of its life, when the core collapses under its own gravity, UY Scuti will reach a tipping point. If the star cannot eject enough mass before collapse, the core will implode into a black hole. This transformation from one of the largest visible structures in the galaxy to a point of infinite density is not just a physical transition, it is an existential one. It highlights the absurd extremes the universe allows, a star that once spanned billions of kilometers reduced to a singularity smaller than a pinhead. It is the ultimate irony that something so vast can vanish so completely, taking with it all the structure and turbulence of its long life. For now, though, UY Scuti remains in a delicate balancing act. Its core continues to fuse heavier and heavier elements, inching toward iron, the final roadblock in stellar fusion. Each stage of fusion provides less energy than the last, and the core's ability to resist gravitational collapse diminishes. Eventually, fusion ceases, and gravity wins. The outer layers may explode outward in a cataclysmic supernova, leaving a remnant behind that will forever warp space and time. As we continue to observe and analyze UY Scuti, we are not just studying one star, we are exploring the nature of stellar life cycles, the boundaries of physics, and the mechanisms that govern cosmic evolution. UY Scuti is more than a star. It is a symbol of how far our curiosity has taken us, and how much further we still have to go. Every moment that UY Scuti continues to shine, it contributes to a cosmic narrative older than any civilization on Earth. It burns not just as a sphere of gas undergoing nuclear reactions but as a dynamic and essential part of the galactic ecosystem. Its life and eventual death will seed the interstellar medium with the raw materials for planets, moons, and potentially life itself. In this sense, UY Scuti is not isolated, it is connected to us through an intricate web of cosmic cause and effect. Its atoms will one day become the carbon in alien plants, the iron in the core of newborn planets, or the calcium in someone's bones across the stars. Yet what makes UY Scuti truly fascinating isn't just its future, but the astonishing reality of its present. Imagine standing on a hypothetical planet orbiting far enough away to survive its radiant fury, if such a world could exist. The sky would be dominated by a giant that fills the heavens, a titanic blood-red sphere of fire whose presence would dwarf any celestial body visible from Earth. Day and night as we know them would be meaningless. Its luminosity would wash the sky in eternal dusk, its pulsations detectable not just in light but in gravitational fluctuations, magnetic fields, and radiation surges. And those pulsations are more than rhythmic beats, they are signatures of internal struggle. UY Scuti, like many red supergiants, is a variable star. It expands and contracts over periods of hundreds of days, its surface inflating and deflating like a breathing lung of plasma. These movements are driven by changes in energy production deep within the core, and they affect everything from the star's brightness to the distribution of matter around it. The outer layers, tenuous and barely held in place by gravity, drift outward with each expansion, sometimes escaping the star's grip entirely. This process of shedding mass is what will ultimately determine how UY Scuti dies. If it can lose enough material, it might collapse into a neutron star rather than a black hole. But if it holds onto most of its mass, even after shedding its outer layers, it will pass the threshold where no force, not even neutron degeneracy pressure, can resist gravitational collapse. This point of no return is known as the Tolman, Oppenheimer, Volkoff limit, and it separates massive neutron stars from black holes. Where UY Scuti falls on this spectrum is one of the big unknowns. The star's mass, while substantial, is surprisingly modest relative to its enormous size. That's because red supergiants like UY Scuti are extremely diffuse. Their outer envelopes are stretched thin by the internal pressure generated from fusion, and as a result, much of their volume is nearly empty space. If you were to travel through the outer regions of UY Scuti, you would find it far less dense than Earth's atmosphere. This counterintuitive fact is part of why such a star can appear so large without being impossibly massive. Its radius may be immense, but its average density is low, so low that a spaceship could, in theory, navigate the star's outer layers without being instantly vaporized, provided it could withstand the heat and radiation. These ideas push the limits of not just astrophysics but human imagination. The numbers associated with UY Scuti, the distances, volumes, temperatures, are so extreme that they barely register as real. But they are real. The same physical laws that govern your cup of tea also govern the fusion reactions in the star's core. The same gravitational principles that make an apple fall to Earth also ensure UY Scuti doesn't instantly disperse into the void. The beauty of astrophysics lies in this unity. The cosmos and the commonplace are governed by the same set of rules, scaled up to unimaginable proportions. Another profound aspect of UY Scuti is the timescale it represents. Stars like it live fast and die young, at least in cosmic terms. While our Sun is expected to live for about 10 billion years, UY Scuti's lifespan is likely less than 10 million years. That's 1,000 times shorter, a cosmic sprint compared to the Sun's marathon. And it's already deep into its life cycle. If UY Scuti were born in the time of the first human ancestors, it would be long gone by now. It might be gone already, its light still traveling toward us across the gulf of time, making us observers of a ghost. This temporal delay adds a surreal quality to astronomy. We never see stars as they are, we see them as they were. When we gaze upon UY Scuti, we are looking at ancient light. Any event that has taken place there since the time of the ancient Roman Empire remains invisible to us. If it has already gone supernova, the shockwave is still racing toward us through interstellar space, but we won't know it until the light finally arrives. In that sense, astronomy is a kind of time travel. Our telescopes are instruments not just of sight, but of memory. Understanding stars like UY Scuti also teaches us about the cosmic hierarchy. Our place in the universe becomes more humbling the deeper we look. Earth, with all its complexity, is a speck of dust orbiting a relatively ordinary star. And yet here we are, sentient beings studying the life and death of objects so vast we can barely comprehend them. This capacity, to reach beyond our planet and understand the workings of a star halfway across the galaxy, is one of the most awe-inspiring aspects of human civilization. It speaks to a deep and relentless curiosity, a drive to explore and explain. And UY Scuti rewards that curiosity. Every new observation, every data point, every improvement in telescope technology brings us closer to understanding how such giants live and die. Missions like the James Webb Space Telescope and the Extremely Large Telescope, ELT, promise even deeper insights. These instruments can peer into the dusty cocoons of red supergiants, analyzing light that has traveled thousands of years to reach us. They can study not just the stars themselves, but the remnants they leave behind, nebulae glowing with ionized gas, expanding shells of debris, neutron stars or black holes spinning silently in the dark. The remains of UY Scuti, whatever form they take, will endure long after the star is gone. They may drift through space for billions of years, touching new star systems, altering planetary chemistry, and perhaps seeding the raw ingredients for biology. This is the grand cycle of matter. Stars are born, they live, they die, and they leave behind the building blocks for future generations of stars and planets. UY Scuti, for all its extraordinary scale, is part of this larger narrative, a story of birth, death, and transformation that unfolds over the lifespan of the universe. And we are watching. We are watching, not with mere eyes but with instruments that extend our senses across the gulf of space and time. We are tracking fluctuations in brightness, subtle shifts in spectral lines, and the faint echoes of past eruptions, all signals sent out by a dying titan whose fate is already sealed. UY Scuti has become more than a point of interest. It is a beacon for all that is mysterious, beautiful, and immense about the universe. Each photon that reaches our detectors carries with it a whisper of ancient fire, a flicker of insight into processes that shape galaxies. The study of UY Scuti also highlights the profound role of metallicity in stellar evolution. In astronomy, the term metallicity refers to the fraction of a star's mass that is not hydrogen or helium. Even trace amounts of heavier elements can influence how a star evolves, how it loses mass, and what kind of remnant it leaves behind. A high metallicity star tends to lose mass more easily through stellar winds, possibly affecting whether it ends up as a neutron star or a black hole. Understanding UY Scuti's metallicity is crucial for placing it within the broader framework of stellar physics. Furthermore, UY Scuti serves as a benchmark for understanding the upper limits of stellar size. While it might not be the most massive or the most luminous star, its radius has set records and challenged our theoretical models. In particular, its sheer scale prompts new inquiries into the physics of convective envelopes and the balance between gravitational containment and radiative pressure. Why does it grow so large while keeping a relatively modest mass? Why doesn't it collapse under its own gravity sooner? The answers to these questions lie in the complex interplay of nuclear physics, thermodynamics, and quantum mechanics, fields that converge within the heart of every star. The shape of UY Scuti is also a topic of speculation. Red supergiants often deviate from perfect sphericity, bulging at the equator due to rapid rotation or external gravitational influences. If UY Scuti rotates even slightly, its enormous envelope may be distorted, leading to uneven surface temperatures, irregular brightness variations, and asymmetric mass loss. Observing these phenomena helps refine our models not just for UY Scuti, but for a class of stars whose ultimate explosions influence the structure and chemistry of the galaxy. Its magnetic field, while difficult to detect directly, also plays a role in shaping its life and death. Strong magnetic fields can channel mass loss along particular directions, forming polar jets or equatorial disks. They can affect how convection behaves within the outer layers, altering surface temperatures and spot formation. In the future, sensitive instruments may allow us to map these fields more clearly, revealing yet another layer of complexity to this already enigmatic star. The environment around UY Scuti tells a story of ancient violence and current instability. Its stellar winds form a vast envelope of gas and dust that stretches far into interstellar space. This circumstellar material, rich in carbon, oxygen, and silicates, interacts with ambient radiation fields, producing infrared emissions detectable by space telescopes. These emissions not only inform us about the composition of the material, but also serve as a historical record of the star's recent activity. Each shell, each arc, each clump of dust is a remnant of a past pulsation, an echo of the star's turbulent outer atmosphere. From a galactic perspective, UY Scuti is one of many red supergiants that help recycle matter back into the interstellar medium. This process is essential for the ongoing birth of new stars and planetary systems. Without massive stars like UY Scuti undergoing such extreme evolutionary changes, galaxies would lack the raw materials needed to create complex chemistry, and by extension, life. The iron in your blood, the calcium in your bones, the silicon in your phone screen, all were forged in ancient stars that lived and died like UY Scuti. And yet, despite all we know, UY Scuti still manages to hide secrets. For instance, estimating its true radius remains a challenge due to the nature of its extended atmosphere and the limitations of current observational techniques. Different wavelengths yield different apparent sizes, creating a range of values that sometimes conflict. This ambiguity highlights how even our most advanced tools are sometimes dwarfed by the sheer complexity of stellar structure at massive scales. New advancements in interferometry, spectroscopy, and space-based imaging will likely sharpen our view. Observatories like the Very Large Telescope, VLT, the Atacama Large Millimeter/Submillimeter Array, ALMA, and the James Webb Space Telescope are already pushing the boundaries of what's possible. These instruments can resolve the extended atmospheres of supergiants, detect the signatures of specific molecules, and even measure the velocities of stellar winds with astonishing precision. With each new dataset, our model of UY Scuti becomes more detailed, more accurate, more complete. But science is not just about facts, it's about meaning. What does UY Scuti represent in the grand narrative of the universe? It is, perhaps, a reminder that creation and destruction are inseparable, that beauty can emerge from instability, and that even the most enormous stars have lifespans that are fleeting compared to the age of the cosmos. It is a burning monument to impermanence, and yet, paradoxically, to cosmic continuity. The elements it creates will survive long after the star itself has vanished from view. Even the act of studying UY Scuti reflects something beautiful about us. We are small, temporary beings clinging to the surface of a fragile planet, and yet we dare to reach across the stars in search of understanding. We look at UY Scuti not just as a ball of gas and fire, but as a question: how do things become so large? How do they end? And what happens next? Every supernova is a punctuation mark in the sentence of cosmic history. When UY Scuti finally explodes, it will write its chapter with a flash of light visible across galactic sectors, with neutrino bursts that may rattle our detectors, with gravitational ripples that may tug faintly at our space-time. We will read that chapter, record it, and remember it. The star will be gone, but the story will remain. And in that story lies not just the tale of a star, but the story of us, curious, searching, ever watching. That story continues not just through observation, but through simulation, through the digital recreation of stellar life cycles inside the memory of our most powerful computers. Astrophysicists use complex models to simulate UY Scuti's internal structure, tracking how hydrogen fuses into helium in its core, how pressure and gravity interact in a constant tug-of-war, and how layers of burning shells stack like nesting dolls as the star nears the end of its life. These models often require supercomputers, running for days or weeks at a time, to account for the enormous number of variables at play. But even then, they are approximations, educated guesses made through the veil of space and time. And yet, with each iteration, we get closer to unlocking the code of a star's destiny. At this level of detail, even the tiniest influences matter. Slight variations in temperature or density can dramatically alter the trajectory of a supergiant's evolution. Magnetic turbulence, quantum mechanical degeneracy, pressure, opacity changes in ionized gases. These are not abstract terms. They are the physics that decides whether a star ends in a fizzle or a cataclysm. For UY Scuti, the margin between different end states is razor thin. One deviation could mean collapse into a neutron star. Another could plunge it into the abyss of a black hole. Meanwhile, its outer layers continue to dance, convecting, pulsating, expelling matter into the interstellar medium like a breathing colossus. These outer convective cells are gigantic, some possibly the size of Earth's entire orbit. They churn over timescales of months or years, boiling the star's photosphere in an endless, violent sea of upwellings and downdrafts. Surface temperatures fluctuate dramatically. One region might cool enough to form dust grains, another may suddenly erupt with energy, blasting particles into the surrounding space. This is stellar weather on a scale beyond comprehension. That weather, in turn, creates shock waves that ripple through the circumstellar environment, disturbing dust clouds and sculpting arcs, rings, and filaments of glowing gas. We have seen these phenomena in stars like Betelgeuse and VY Canis Majoris, and it's likely UY Scuti is surrounded by similar evidence of its own fury. These structures provide clues to its mass loss history, records of previous eruptions encoded in the material it ejected. It is a scrapbook of stellar suffering, catalogued in arcs of carbon monoxide and silicate dust. Moreover, the chemistry of these ejected materials hints at something deeper. Red supergiants like UY Scuti are factories of complex molecules. Their cool outer layers are perfect environments for creating compounds like water vapor, silicon monoxide, and even organic molecules. These molecules drift into space, forming the seeds of future solar systems. The materials that make up comets, planets, and potentially even the building blocks of life often start in places like this, in the burning breath of dying giants. In a very real sense, the story of UY Scuti is the prelude to the story of other worlds. And yet, we have never seen it explode. We do not know when its life will end. It could be in 1,000 years, or 10,000, or even longer. The timescales of stellar evolution dwarf human lifetimes. All our technology, all our models, all our waiting might not be enough to catch its final moments. But when that day does come, it will be a spectacle etched across the galaxy. A supernova of this magnitude could outshine the entire Milky Way for weeks. Its remnants, neutron star or black hole, would linger as a cosmic gravestone. Even after death, it will not be truly gone. The shockwave of the explosion will travel outward, stirring the interstellar medium and compressing gas clouds, triggering new generations of star formation. In this way, UY Scuti's demise could give birth to dozens, even hundreds of new stars. Its legacy would be scattered across the night sky, a family of suns tracing their lineage to one dying giant. This, too, is part of the cosmic cycle, a dance of creation and destruction that has played out for billions of years. Stars are not isolated actors. They are nodes in a network of cosmic cause and effect, influencing their neighbors, shaping galaxies, building and destroying in equal measure. UY Scuti is not just one of the largest stars we know, it is a turning point in this eternal chain reaction. And the human mind, small though it may be, is powerful enough to contemplate this. To track it. To model it. To name it. That act, of naming the unknown, is a kind of defiance against cosmic silence. When we say, UY Scuti, we are not just referencing a catalog entry in a stellar database. We are telling a story of matter and light, of time and collapse, of death and rebirth. So we keep watching. We peer through infrared filters and parse radio signals. We map the dust, chart the molecules, track the temperature curves. We compare it to other red supergiants. We refine our techniques. We theorize. We dream. And as we do, the star continues its slow decline. Not with a whimper, but with majesty. A sun so vast it defies imagination, yet bound by the same laws of physics that govern our own. And in that majesty lies a paradox. UY Scuti, despite its scale, remains fundamentally ephemeral. It will burn through its final fuel and perish far sooner than a smaller, dimmer star. While tiny red dwarfs can last for trillions of years, UY Scuti may survive only for a few million, a cosmic blink. Its size is its strength, and its downfall, a candle burning furiously bright and short. It serves as a monument to impermanence, a reminder that even the mightiest forces in nature are not eternal. We do not know precisely how much mass UY Scuti will retain at the time of its death. As it continues to shed its outer layers, its final mass will determine the kind of supernova it will produce and what object will be left behind. If it retains enough core mass, likely above 20 to 25 solar masses, it may collapse into a black hole. If it falls short, it could produce a neutron star instead. This isn't just idle speculation, it's a live question for astrophysics. UY Scuti is a test case for understanding how massive stars end and what cosmic relics they leave behind. But beyond physics and fate, there is philosophy. Consider what it means that a single star, tens of thousands of light years away, can become an object of fascination, study, and metaphor. We name such stars, chart them, assign coordinates and measure flux, but also infuse them with human meaning. UY Scuti is both a scientific object and a poetic idea. It's a metaphor for the limits of scale, for the grandeur and frailty of existence, and for the ultimate unity of matter, from the atoms in your body to the ones in a star's core. Indeed, the hydrogen being fused in UY Scuti today is the same hydrogen that was born during the Big Bang, over 13.8 billion years ago. That ancient gas, scattered through primordial space, clumped into galaxies, fell into clouds, collapsed into stars, and is now burning again. In this way, UY Scuti is not an isolated entity, but a continuation of a thread that runs across time and space. It is a present-tense flame igniting ancient fuel. We are watching the aftershocks of the universe's origin still playing out in real time. And when we point our telescopes toward UY Scuti, we are looking into the past. The light we see from it today has taken nearly 9,500 years to reach us. That means whatever is happening there now is hidden from us for nearly a full millennium. The star could already be gone, and we wouldn't know. The idea that we might be seeing the ghost of a star that no longer exists is not just chilling, it's deeply humbling. It means that time, light, and knowledge are never perfectly aligned. This time lag also adds a strange dramatic irony to the study of stars. Our observations are always delayed. Our models are always retroactive. We chase shadows cast by events long concluded. Yet even these shadows can be illuminating. In the patterns of stellar spectra, in the fluctuations of brightness, in the arcs of dust and filaments of gas, we read the biographies of giants. And from these we draw the arc of all stellar life. UY Scuti has already rewritten parts of that biography. Its initial designation in the second Uppsala General Catalogue, hence UY, in UY Scuti, classified it as a simple variable star. It was just one of many flickering red lights catalogued by astronomers. But as data improved and telescopic precision increased, its scale began to stand out. When infrared measurements revealed the true scope of its bloated atmosphere, the astronomical community had to take notice. This was not just a variable, it was potentially the biggest star we had ever found. Size, of course, is always contextual. UY Scuti is currently considered one of the largest by radius, not by mass. Mass-wise, other stars far exceed it, especially Wolf-Rayet stars and blue hypergiants, which are small in size but dense in substance. But in terms of sheer volume, of how much space its outer atmosphere occupies, UY Scuti reigns supreme or close to it. That difference matters. It reminds us that big in space is not a single dimension. Stars can be massive but compact, or huge and diffuse. This diffuseness matters greatly for how we understand UY Scuti's structure. Its outer layers are so extended and low in density that calling them a surface is misleading. The edge of the star is more like a fading gradient of matter, not a solid boundary. The photosphere we see is just a layer where the gas becomes transparent enough to emit light freely. It's not a wall or shell. As you travel inward, the temperature and pressure slowly ramp up, until nuclear fusion roars in the core. That core, likely surrounded by concentric shells of different fusion processes, is where the real action happens. In stars like UY Scuti, hydrogen fusion in the core eventually gives way to helium burning, which then cascades through heavier elements, carbon, neon, oxygen, and so on, until iron is formed. Iron is the end of the line. Fusing it absorbs energy instead of releasing it. And when iron accumulates, the balance between outward pressure and inward gravity fails. The star collapses catastrophically. This is the death spiral for massive stars. The core implodes, outer layers rebound and explode, and a supernova is born. For UY Scuti, this moment will be especially violent due to its size. The explosion will release more energy in a single event than our Sun will emit in its entire 10 billion year lifetime. And the resulting remnant will be a gravitational beast, a collapsed object with gravity so strong it warps the fabric of space-time. If it becomes a neutron star, it will be a city-sized object with the mass of the Sun, spinning rapidly and emitting beams of radiation like a cosmic lighthouse. If it becomes a black hole, it will be an invisible well in space-time, a place from which nothing, not even light, can escape. Either way, UY Scuti's core will persist, compacted into a new form, even as the rest of the star is strewn across the galaxy. That galactic dispersal is more than poetic. It's ecological. The heavier elements created in UY Scuti's fusion cycles, carbon, oxygen, magnesium, silicon, will be ejected into space. These elements are the raw ingredients for planets, moons, comets, and life. Every atom of calcium in your bones, every trace of iron in your blood, was likely forged in a star like UY Scuti. We are, quite literally, made of stardust. When UY Scuti dies, it will return that dust to the galactic commons. This is not just a metaphor. It's an empirical truth. Spectroscopic analysis of the gas and dust in interstellar clouds reveals signatures of past supernovae. Meteoritic isotopes show evidence of decay from radioactive elements forged in ancient stellar cores. Planetary systems, including our own, contain materials that must have come from massive stars. In this way, UY Scuti's story is our story. Its death is a prerequisite for birth. So we study it. We point ALMA and VLT and Hubble and soon, James Webb and beyond toward it. We look in the infrared, the submillimeter, the radio bands, seeking ever clearer images of its atmosphere, its environment, its variability. We log every dimming, every flare, every spectral anomaly. We simulate it in silicon, imagine it in theory, chase it across wavelengths. All because this one red colossus holds a key to understanding how stars live and die. Even the very act of observing UY Scuti presents challenges that highlight how complex stellar study truly is. Its tremendous size means its outer layers are tenuous, turbulent, and constantly shifting. These fluctuations create irregularities in brightness that confuse simple classification. Unlike small, stable stars, the outer shell of UY Scuti may pulse with convection, vast plumes of gas rising and falling across distances greater than the orbit of Jupiter. These surface movements give rise to observable variability, but decoding the exact patterns is a science unto itself. Astronomers track this variability through light curves, graphs that plot the intensity of light emitted by the star over time. For UY Scuti, these curves reveal dips and peaks that correspond to pulsation cycles. However, the pulsations are not always consistent. There are long periods of irregular behavior, changes in amplitude, and shifts in cycle lengths, all of which point to a dynamic, evolving envelope. Such behavior is characteristic of red supergiants, but it is magnified to extreme degrees in hypergiants like UY Scuti. Some of these changes may be tied to the star's attempts to maintain hydrostatic equilibrium, its internal balancing act between the outward pressure from fusion and the inward pull of gravity. As different layers of the star burn at different rates, the balance wobbles. The result is a bloated, convective outer atmosphere that can grow and shrink, flare and fade, like a living thing breathing through eons. And as the outer layers shift, so too does the visible radius. UY Scuti's radius is not a fixed line, it's more of a moving boundary that changes depending on wavelength, method of observation, and the star's own internal activity. That's why radius estimates vary between sources. The atmosphere is so diffuse and transparent in some regions that measuring a precise edge is virtually impossible. Infrared measurements might show one size, radio another, and visual light yet another. Even more fascinating is the role played by dust. UY Scuti sheds material at such a high rate that it is surrounded by a thick circumstellar dust shell, an envelope of soot-like grains formed from elements expelled in stellar winds. These dust grains absorb and scatter light, particularly in the visible spectrum, creating a halo that both conceals and reveals. Observing in infrared allows astronomers to peer through this dust and gain clearer insights into the structure of the star and its surroundings. The dust is not just a nuisance, it's a data source. By studying the composition, temperature, and distribution of the dust, astronomers can reverse engineer the chemistry of the star's outer layers. This process, known as spectroscopy, involves breaking down light into its component wavelengths and identifying the fingerprints of elements and molecules. For UY Scuti, this has revealed the presence of silicates, carbon compounds, and other minerals that hint at the ongoing processes of mass loss and chemical evolution. Mass loss, in fact, is one of the defining features of UY Scuti's life stage. The star is losing mass at an astonishing rate, likely on the order of several Earth masses per year. Over astronomical timescales, this adds up to a significant depletion of its envelope. This loss alters the star's temperature, luminosity, and lifespan, while enriching the interstellar medium. It also affects how the star will die, as less mass in the envelope could reduce the violence of its eventual supernova, or shift it into a different category altogether. And then there's the mystery of whether UY Scuti is a single star or part of a binary system. While current evidence points toward it being solitary, many massive stars are part of binary or even multiple systems. Binary interactions can drastically alter a star's evolution. They can strip away outer layers, spin up the core, or trigger episodic outbursts. If UY Scuti has a companion star, hidden behind dust or simply too faint to detect, it could change our entire understanding of its size, behavior, and fate. Indeed, these uncertainties have led some astronomers to reevaluate the title of largest star. While UY Scuti has frequently been cited as the largest known star by radius, other contenders exist. Stars like VY Canis Majoris, Betelgeuse, and Stephenson 2-18 have similar or even greater radii, depending on how measurements are made. The ranking can shift as new data comes in, highlighting how dynamic and data-dependent this field is. Still, UY Scuti remains an icon, a symbol of stellar immensity and complexity. Beyond the physics, there is a cultural and historical layer to UY Scuti's fame. It has become a staple of popular science discussions about the cosmos. Its staggering size makes it a favorite comparison tool, used to illustrate the scale of stars, the limits of human comprehension, and the vastness of the universe. Articles, videos, books, and lectures have all invoked UY Scuti as a way to shock and awe audiences into appreciating cosmic immensity. But that fame is not without risk. Simplified depictions can sometimes obscure the science. For example, many graphics showing UY Scuti compared to the Sun depict it as a clean sphere, but in reality, the star is lumpy, distorted, and asymmetrical. Its rotation, convection, and mass loss give it a shape more akin to a wrinkled balloon than a perfect orb. Additionally, its radius is often quoted without caveats about measurement methods or wavelength dependencies, leading to misconceptions about its physical nature. That's why it's so important to approach UY Scuti not just as a wonder, but as a scientific case study. It is a laboratory in the sky, teaching us about convection, mass loss, stellar winds, nuclear fusion, and the life cycles of the most massive stars. It challenges our models, expands our understanding, and reminds us that even our best telescopes are still peering through a fog of uncertainty. The more we learn, the more questions arise. Some of those questions are deeply theoretical. For instance, what exactly triggers the transition from red supergiant to core collapse supernova? How do convection and rotation interact in a star with such an immense radius? What role do magnetic fields play in channeling stellar winds and ejecting mass? And how do we reconcile observational data with models that often assume symmetry and simplicity in stars that are anything but? Answering these questions requires multi-wavelength observation campaigns, high-resolution spectroscopy, 3D hydrodynamic simulations, and more. It requires the use of cutting-edge observatories like the James Webb Space Telescope, which can pierce through the dust and reveal the deeper layers of the star and its surroundings. It requires collaboration between theorists, observers, and modelers, all working to decode the secrets of a single, flickering giant. But perhaps the most profound thing about UY Scuti is what it reveals about us. The very act of studying such a distant and ephemeral object reflects something essential about human curiosity. We are creatures who look up, who ask questions, who build instruments to gather the faintest traces of light from the farthest corners of the sky. In studying UY Scuti, we are not just learning about stars, we are fulfilling an ancient instinct to understand our place in the universe. And that instinct leads us further. Because UY Scuti is not alone. It is one of billions of stars in the Milky Way, and one of trillions in the universe. Each has a story, a life cycle, a unique path through time and space. Some will be short-lived fireballs, others slow-burning embers. Some will end in quiet collapse, others in titanic explosions. Some will leave behind planets, others nothing at all. UY Scuti is simply the most extreme among them, a reminder of what stars can be when all the variables align. It is a window into extremes, of size, heat, age, distance, and destiny. And like all such windows, it demands humility. As much as we now know about it, UY Scuti continues to evolve, to shed, to pulse, and possibly to surprise. One day, perhaps soon in astronomical terms, it will die. When it does, it will light up the sky of its region in a blaze that echoes across space. And thousands of years later, that light may reach Earth. Long after we are gone, UY Scuti may send its final message across the stars. That final message, UY Scuti supernova, will not be just a burst of energy, but a cosmic punctuation mark in the ongoing story of stellar evolution. When such massive stars reach the end of their lives, they undergo collapse in mere seconds. The core, unable to support its own weight, implodes under gravity, creating conditions so extreme that atoms are crushed and neutrinos are released in vast numbers. For UY Scuti, this collapse would unleash an explosive rebound, a supernova, a detonation of unimaginable power. The outer layers would be ejected into space at speeds exceeding 10,000 kilometers per second, blasting heavy elements like iron, silicon, and nickel into the interstellar medium. These are the raw materials that future stars, planets, and life itself will be made of. In this way, UY Scuti would not just end its life, it would seed the galaxy with the building blocks of creation. That is the poetic irony of stellar death. In dying, a star like UY Scuti becomes a birthplace. What will be left behind after the explosion? That depends heavily on UY Scuti's final mass at the moment of collapse. If the core remaining after the outer envelope is shed is under a certain threshold, about 2 to 3 solar masses, it may become a neutron star. Neutron stars are incredibly dense remnants composed almost entirely of neutrons, packed so tightly that a single teaspoon would weigh billions of tons. They spin rapidly, emit beams of radiation, and are often observed as pulsars, flashing beacons of collapsed matter. However, UY Scuti may go one step further. Given its immense starting mass and the uncertainty of how much it will lose before dying, it's possible that the remnant core will be massive enough to avoid stabilizing as a neutron star. In that case, the core would continue collapsing until it forms a black hole, a singularity of infinite density surrounded by an event horizon from which nothing, not even light, can escape. That would be UY Scuti's ultimate fate, not just to die, but to vanish. A black hole born from such a star would linger silently, invisible yet influential, shaping the space around it, pulling in gas, dust, and perhaps even unfortunate stars that stray too close. It would become an invisible punctuation mark on the galactic map, detectable only by its gravitational effects or the X-rays emitted by infalling material. From blazing supergiant to lightless void, UY Scuti's life would come full circle, from creation to destruction to silence. But before that day arrives, UY Scuti continues to burn. Its surface fluctuates with convection, its atmosphere spills into space, and its massive heart fuses heavier and heavier elements in a furious race toward collapse. Each second, it releases more energy than our sun does in an entire year. And yet, it exists at such a distance, approximately 9,500 light-years away, that all of that fury registers as a faint, reddish twinkle in the constellation Scutum. To the naked eye, it is nearly invisible. But through the lens of science, it is monumental. The distance to UY Scuti adds to its mystique. Light from the star takes millennia to reach us, meaning we do not see the star as it is, but as it was thousands of years ago. It is possible, though unlikely, that UY Scuti has already exploded and we simply haven't seen it yet. This delay in light transmission gives rise to one of the most haunting truths of astronomy. Everything we observe is a glimpse into the past. We are time travelers looking backward, piecing together stories from ancient light. And what a story UY Scuti tells! It began its life as a massive protostar, perhaps 20 to 40 times the mass of our Sun, forming in a dense region of a molecular cloud. Gravity compressed the gas and dust until nuclear fusion ignited in its core. From there, it entered the main sequence, burning hydrogen and settling into a state of equilibrium. But with such a high mass, it could not linger long in that peaceful state. It raced through its life stages, burning through hydrogen, then helium, and then progressively heavier elements. Each stage was shorter than the last. While smaller stars like the Sun spend billions of years on the main sequence, stars like UY Scuti live fast and die young. It may have existed for only a few million years, just a blink on the cosmic calendar. The end comes swiftly for such giants, as iron accumulates in the core and fusion grinds to a halt. Without fusion pressure to counteract gravity, collapse becomes inevitable. And then, the supernova, the blast, and the remnant. For now, though, it is in its supergiant phase, a period marked by instability, mass loss, and extreme luminosity. And in this stage, it contributes to science in countless ways. Studying UY Scuti helps refine our models of stellar atmospheres, supernova progenitors, and mass ejection mechanisms. It helps calibrate distance measurements, contributes to galactic chemical evolution, and challenges our understanding of stellar structure. It is a teacher, as well as a spectacle. Telescopes continue to watch it. Some use adaptive optics to correct for atmospheric distortion and sharpen the star's image. Others observe in the infrared or radio spectrum, peering through dust and uncovering hidden features. Space-based observatories, free from Earth's atmospheric limitations, provide some of the clearest data yet. These instruments allow scientists to monitor variability, detect circumstellar material, and map the star's outflow patterns. And the data keeps flowing in. One recent finding suggests that UY Scuti's variability may be linked not just to pulsations, but to large-scale convective cells, gigantic blobs of gas rising and falling across its surface. These convective cells may be so large that they span a third of the star's diameter, causing surface dimming and brightening as they rotate into and out of view. This challenges our understanding of stellar surface dynamics, and opens new avenues of exploration. Even more recently, simulations suggest that stars like UY Scuti may undergo episodic mass loss events, periods of sudden, violent shedding triggered by internal instabilities or rotational effects. These episodes could create expanding shells of gas and dust, observable as arcs or rings in the surrounding nebula. Detecting and studying these features can help astronomers pinpoint when and how the star is approaching the end. But in all of this, there is one constant: awe. To consider a star like UY Scuti is to confront the immensity of the universe, the fragility of life, and the beauty of science. It represents the upper bound of what nature can do with hydrogen, gravity, and time. And yet, it is not unique. It is one of many such giants scattered across the cosmos, each with its own story, each waiting to be understood. And so, the watch continues. Scientists observe. Theories evolve. Instruments improve. And UY Scuti, silent and immense, drifts on, its light echoing across time, its legacy growing with every new discovery. One day, perhaps centuries or millennia from now, a brilliant new light will appear in the sky, the final act of a star that spent its life trying to outshine all others. In that moment, when the light from UY Scuti's death finally arrives at Earth, the night sky will change forever. To the untrained eye, it may appear as a new star, bright enough to be seen during the day, possibly outshining the moon. To astronomers, it will be a long-awaited cosmic event, an opportunity to observe a core collapse supernova in exquisite detail, to study the physics of matter under extreme conditions, and to confirm, or challenge, our most advanced theories about the lives of massive stars. But even before that cataclysmic finale, UY Scuti offers a rich array of mysteries. The sheer size of its radius, estimated at around 1,700 times that of our Sun, raises questions about the precise mechanisms that allow a star to balloon to such immense proportions without tearing itself apart. At such a scale, its outer layers are only tenuously bound by gravity. A photon emitted from its core may take thousands of years to reach the surface, its journey slowed by countless interactions with particles, scattering through an opaque plasma until it finally escapes. By the time it reaches us, it tells a story that is millennia old. The low surface gravity at such a massive radius contributes to a phenomenon known as stellar wind, a continuous stream of particles being ejected into space. These outflows of gas create an expanding envelope around the star, rich in molecules and dust. Over time, these winds accumulate to form a circumstellar nebula, a shell of material that surrounds the star like a veil. Observing these nebulae can reveal the star's history of mass loss, highlighting moments of quiescent shedding or violent upheaval. These features also contribute to the broader cycle of matter in the galaxy, enriching the interstellar medium with complex molecules and helping to seed new star-forming regions. UY Scuti's composition is another field of active study. Like most massive stars, it began its life primarily composed of hydrogen and helium. As it aged, nuclear fusion in its core began to create heavier elements: carbon, oxygen, neon, magnesium, and eventually iron. These fusion processes proceed in shells, much like the layers of an onion, with each layer fusing a different element. This layered structure is both elegant and perilous. As the core becomes heavier and denser, fusion reactions become faster and more unstable. Once iron accumulates at the center, fusion can no longer produce energy. Iron fusion consumes energy instead of releasing it, dooming the star to gravitational collapse. During these final stages, UY Scuti will fuse heavier elements in mere days or even hours. What took millions of years to evolve will unravel in a cosmic heartbeat. The moment the iron core reaches a critical mass, the star will implode, and the subsequent explosion will outshine entire galaxies for a brief time. Observing this will offer a window into the very physics of collapse, shockwave propagation, and element synthesis. But even before that climactic end, there is the enigma of the star's variability. UY Scuti is classified as a semi-regular variable star, which means that its brightness fluctuates over time. These fluctuations are not entirely random, but they are not perfectly periodic either. They're driven by pulsations, expansions and contractions in the star's outer layers. These can be caused by internal instabilities or by changes in radiation pressure. Understanding these pulsations helps astronomers map the star's internal structure. It's a bit like listening to seismic waves to understand the Earth's interior, except these are light waves from a star halfway across the galaxy. The radius of UY Scuti also depends on its variability. When astronomers say the star is about 1,700 times the radius of the Sun, they are giving an average. Its size changes depending on the phase of its pulsation. Some measurements, taken during a contraction phase, suggest a radius closer to 1,400 times the Sun's. Others, during expansion, suggest figures approaching 1,800. This variability makes it difficult to pin down an exact number, but it also adds to the star's intrigue. It's a living system, constantly in motion, breathing in and out on a cosmic scale. There is also the question of how UY Scuti compares to other titans. For many years, it held the title of largest known star by radius. That title has since been challenged by other red supergiants and hypergiants, such as VY Canis Majoris and Westerlund 1-26. But each contender has its own caveats. Some are larger but farther away and harder to measure precisely. Others are more massive but less voluminous. What makes UY Scuti exceptional is the balance of its immense size, relative proximity, and the amount of data we have on it. We must also consider its role in the galactic ecology. UY Scuti, like all massive stars, serves as a kind of cosmic forge. It is an engine of alchemy, transforming hydrogen into helium, helium into carbon, and so on up the periodic table. These processes create the elements that will one day become planets, oceans, atmospheres, and living beings. The oxygen we breathe, the calcium in our bones, the iron in our blood, all were forged in the heart of a star like UY Scuti. It is, in the most literal sense, an ancestor of life. Yet UY Scuti is also a symbol of impermanence. It reminds us that even the largest and most powerful entities in the cosmos are transient. It exists for a brief moment on the cosmic timeline before giving way to entropy. But in its short life, it shines more brightly and influences more matter than smaller stars could in billions of years. It is a flash of brilliance on a galactic stage, a singular moment of grandeur in an otherwise dark universe. The star also raises philosophical questions. When we gaze at UY Scuti, we are not just looking across space, we are looking across time. The photons hitting our telescopes today began their journey long before the rise of human civilization. Some of them set out before the construction of the pyramids, before the first cities, before language itself. To witness UY Scuti is to witness a relic of deep time, a message from the ancient universe. In a way, this makes the star a storyteller. Its light carries with it the record of fusion, expansion, turbulence, and change. It is a glowing fossil, radiating the narrative of its own life across the abyss of space. And we, tiny beings on a pale blue dot, have built instruments sensitive enough to decode that light, to translate its flickers and wavelengths into knowledge, insight, and awe. And we are just beginning. With future telescopes like the Extremely Large Telescope, ELT, and the James Webb Space Telescope already in operation, we will be able to study UY Scuti with even greater clarity. We'll be able to observe finer details of its surface, probe its dust envelope, and perhaps even map the geometry of its convection cells. These insights will not just tell us more about UY Scuti, they will tell us more about all stars. Because in understanding the extremes, we understand the rules. So as the centuries pass and humanity continues to reach outward into the cosmos, UY Scuti will remain a guiding light, literally and figuratively. It will serve as a touchstone for our understanding of stellar physics, a benchmark for the limits of size and brightness, and a poetic reminder of the grandeur and transience of the universe. It is a cosmic cathedral of gas and fire, towering in the heavens, ancient and immense, serene and violent. And when it dies, the universe will change, not because it notices, but because we do. The death of UY Scuti will not merely be the end of a single star. It will be a celestial punctuation mark in the grand narrative of the Milky Way. When its supernova erupts, it will send out shockwaves that will travel across interstellar space, compressing gas and dust clouds, potentially igniting the birth of new stars in nearby regions. In this way, UY Scuti's death becomes a form of cosmic recycling, a magnificent destruction that leads directly to creation. This process, known as triggered star formation, is one of the great paradoxes of the universe. Death breathes life on a galactic scale. These shockwaves will also be loaded with heavy elements, synthesized in the final seconds of the star's life. Gold, uranium, and other rare elements will be flung into the galaxy. These are the same atoms that later get incorporated into future planetary systems. In fact, the very presence of such elements on Earth hints at ancient supernovae that exploded long before our sun was born. It's not hyperbole to say that the gold in a wedding ring, or the iodine in your thyroid could have originated in a supernova from a star like UY Scuti. Its final act will not be an end but a transformation, one that leaves its fingerprints on everything that follows. And let's consider the neutrino burst that will accompany UY Scuti's supernova. In the seconds before its explosion becomes visible, the collapse of its core will produce an immense stream of neutrinos, ghost-like particles that barely interact with matter. These particles will pass through planets, moons, and stars unnoticed, but sophisticated detectors here on Earth will catch a whisper of this subatomic storm. That first wave of neutrinos could serve as an early warning system, alerting astronomers to turn their eyes toward the sky before the light even arrives. It will be like hearing a thunderclap before seeing the lightning, a rare glimpse of cause before effect. But perhaps one of the most haunting aspects of UY Scuti's inevitable fate is the uncertainty surrounding the exact manner of its death. While many predict a core collapse supernova, some theories suggest a more exotic possibility. If the star's core is massive enough, it might collapse directly into a black hole, bypassing the explosive phase almost entirely. In such a case, UY Scuti could simply vanish from the sky, a ghost star swallowed whole by gravity, leaving behind little more than gravitational waves and silence. Gravitational waves are ripples in the fabric of space-time itself, and their detection from such an event would mark another monumental scientific milestone. These waves move at the speed of light, yet distort the very medium through which light travels. If UY Scuti collapses into a black hole, it could provide a clear and focused signal for detectors like LIGO and Virgo, offering a unique opportunity to observe the birth of a black hole in real time, a feat humanity has never accomplished from a known, pre-collapse massive star. And even if it doesn't collapse into a black hole, its post-supernova remnant will still be an object of intense interest. If a neutron star forms instead, it would be an ultra-dense object only about 20 kilometers wide but with a mass greater than the Sun. A single teaspoon of its matter would weigh billions of tons. This neutron star could be a pulsar, emitting precise beams of radiation as it spins, acting as a kind of cosmic lighthouse that astronomers can track for eons. Or if conditions are right, it might even become a magnetar, a neutron star with a magnetic field so intense it could erase data on credit cards from thousands of kilometers away. Beyond the physical remains, UY Scuti will also leave behind an observational legacy. Its data will be stored in terabytes across digital archives, poured over by future generations of astronomers. Every measurement, every spectral analysis, every time series observation will serve as a case study in stellar evolution. Students yet unborn will learn about red supergiants by studying UY Scuti. Its name will be etched not only into the cosmic ledger of the Milky Way, but into textbooks, lectures, simulations, and even fictional representations of giant stars. Its influence also extends into the realm of public imagination. For those who aren't professional astronomers, UY Scuti represents something almost mythical, the very limit of how massive and bloated a star can become before the laws of physics intervene. It is a reminder that the universe is not just big, but staggeringly, incomprehensibly immense. The fact that such an object exists at all expands the horizon of what we believe to be possible. It challenges our perceptions, not just of the stars, but of our place among them. This influence has seeped into art, music, literature, and philosophy. Writers use UY Scuti as a metaphor for unreachable grandeur. Artists visualize it as a roiling crimson furnace, defying proportion and scale. Composers imagine its pulsations as slow, deep echoes in galactic symphonies. In every field of human expression, this enormous star finds a home, its image acting as a canvas for existential exploration. After all, if UY Scuti can exist, if something that huge, that bright, that unstable can live and die in the void, what else might the universe be hiding? UY Scuti also intersects with the history of human discovery. In the past, we mapped the stars by eye. Today, we use satellite observatories and space-based instruments, parsing spectra with algorithms and AI. But UY Scuti bridges these eras. Though it was catalogued in modern times, its awe-inspiring scale makes it feel ancient, almost mythological. It's a celestial monument standing on the edge of what we can understand, and as our tools grow sharper, we carve deeper into its mysteries. And let's not forget its galactic context. UY Scuti resides in the Scutum constellation, near the center of the Milky Way. Its position gives it a vantage point closer to the galactic core, a region bustling with activity, dense star fields, black holes, and vast molecular clouds. Observing UY Scuti is like looking out from a cosmic balcony over the heart of the galaxy. From its neighborhood, the sky would be filled with light, denser and richer than anything we see from our corner of the galactic suburbs. This setting adds yet another layer to its mystique, a giant among giants, presiding near the heart of our spiral galaxy. As astronomers continue to observe it, new questions arise. What role did UY Scuti play in its local environment over the millennia? Has it influenced the structure of nearby clouds or the formation of young stars? What can its spectrum tell us about the life cycle of massive stars? Or about the initial mass function that governs how stars form in different parts of the galaxy? Each new observation peels back another layer, revealing both answers and deeper puzzles. Its mass, too, is a point of fascination. While its radius is among the largest ever measured, UY Scuti is not the most massive star we know of. Stars like our 136A1 far outweigh it in terms of mass, yet they are more compact and hotter. This illustrates a subtle but vital distinction: mass does not always correlate with size. UY Scuti is large because it is old, because its outer layers have expanded over time due to changes in pressure and temperature as it nears the end of its life. Understanding this distinction helps astronomers refine their models of stellar structure and evolution. Every time a new measurement is taken, whether it be a slight change in brightness, a shift in spectral lines, or a variation in radio emissions, we update our mental picture of UY Scuti. It's not a static entity, it's a dynamic system, always changing, always evolving. It's a conversation between mass and energy, pressure and gravity, creation and collapse. In this dialogue, the universe whispers its most profound secrets. And in those whispers, we hear echoes of ancient truths and emerging revelations, for UY Scuti is more than a singular entity. It is a living archive of the universe's grandest processes. Its surface pulses with the chaotic rhythms of thermonuclear reactions occurring deep within its core. These pulsations, subtle yet powerful, cause the star to vary slightly in brightness over time, revealing invaluable clues about the internal structures and pressures balancing this cosmic giant on the knife's edge of gravitational collapse. Studying these pulsations, classified as semi-regular variables, allows astrophysicists to build detailed models of the star's interior, a task that cannot be performed by direct observation due to the immense distances involved. These models are like seismic maps, akin to how scientists study earthquakes on Earth to infer the planet's inner layers. For stars, this field is called astroseismology, and UY Scuti, with its immense girth and deep oscillations, serves as a particularly rich subject. Every tiny flicker of its light becomes a data point in understanding not just itself, but stellar behavior more broadly. Its chemical composition is another avenue of discovery. The outer layers of UY Scuti, having expanded and cooled over time, allow astronomers to detect a wide array of elements in its atmosphere. Through spectroscopy, they identify absorption lines that correspond to hydrogen, helium, carbon, oxygen, and heavier elements formed during the star's internal fusion cycles. These spectral lines act like barcodes, unique identifiers that reveal the presence and abundance of specific elements. This information not only enriches our understanding of UY Scuti's life stage, but it also helps us piece together the history of stellar nucleosynthesis, the cosmic process by which the elements that compose everything we know, including us, were forged. And this aspect, the origin of elements, cannot be overstated. Every atom heavier than hydrogen and helium was formed in the belly of a star or during its explosive demise. Iron in your blood, calcium in your bones, oxygen in your lungs, all were synthesized in the heart of a dying star. UY Scuti, as it continues to burn through its remaining fuel, is actively creating new elements that will eventually be released into the interstellar medium, enriching future generations of stars and planets. It is a stellar alchemist, converting raw hydrogen into the building blocks of complexity, generation after generation. Consider, too, the notion of timescales. UY Scuti has likely existed for millions of years, far longer than human civilization, yet just a blink in the 13.8 billion-year history of the universe. Stars like this age in a vastly accelerated way compared to our Sun. While our Sun will live around 10 billion years, UY Scuti, by virtue of its size and luminosity, will exhaust its fuel in a fraction of that time. It's a classic cosmic paradox. The larger and more luminous the star, the shorter its life. Like a candle burning brightly, it consumes itself at a voracious rate. Its existence reminds us that brilliance often comes with brevity. And yet, what a brilliant life it is! The energy output of UY Scuti defies easy comprehension. Its luminosity is estimated to be over 300,000 times that of the Sun. This means that in just 1 second, it emits more energy than our Sun does in over 5 days. If placed at the center of our solar system, its swollen photosphere would engulf Mercury, Venus, Earth, Mars, and possibly Jupiter. And while its surface temperature is cooler than that of our Sun, the sheer size of its radiating surface allows it to emit vastly more total energy. It is the embodiment of scale, a body so massive, so luminous, that it breaks the boundaries of common sense. But even that energy is not spread evenly. Like many red supergiants, UY Scuti likely has vast convective cells on its surface, turbulent regions of rising and falling gas, each of which may be larger than Earth itself. These cells transport heat from the star's interior to its outer layers, driving massive currents, and creating patterns of brightness and dimness across its face. In some cases, these convective movements can lead to the ejection of stellar material into surrounding space, contributing to the complex circumstellar environment that surrounds many supergiants. Dust and gas form nebulous halos, further obscuring the star from view and complicating observations. This dusty envelope also plays a role in the apparent brightness of UY Scuti. Since it lies within a dense region of the Milky Way, much of its emitted light is absorbed or scattered by intervening material, making it appear dimmer than it truly is. When corrections are made for this interstellar extinction, its true luminosity emerges, reminding us once again that appearances can be deceiving on the cosmic stage. What seems faint through a telescope may in reality be a roaring inferno, hidden behind veils of cosmic dust. And yet, for all its size and power, UY Scuti is just one among many massive stars in our galaxy. It is notable, certainly, one of the largest ever measured by radius, but it does not exist in isolation. It is part of a continuum, a stellar zoo that ranges from tiny red dwarfs to hypergiants, each with its own story, its own path through the HR diagram. By comparing UY Scuti to other stars, like Betelgeuse, Antares, or VY Canis Majoris, astronomers can identify patterns and exceptions, slowly refining our understanding of stellar evolution. Each observation, each comparison, is like a puzzle piece falling into place. The Hertzsprung-Russell diagram, which plots stars by their luminosity and temperature, serves as a map of stellar life. UY Scuti sits in the upper right, in the domain of cool but highly luminous red supergiants. Its position tells us that it is nearing the end of its life, having exhausted the hydrogen in its core and now fusing heavier elements in increasingly desperate cycles. This region of the diagram is a graveyard of giants, stars that live fast, die young, and leave behind the most energetic remnants in the universe. And from that graveyard, a phoenix may rise. Whether UY Scuti becomes a neutron star or a black hole, whether it explodes in a supernova or collapses in silence, its legacy will be profound. The elements it creates, the shockwaves it sends, the gravitational distortions it causes, all will ripple outward, touching stars, planets, and perhaps even life, in ways we cannot yet imagine. Its role in the cosmic story is not just as a subject of study, but as an actor in a vast, ongoing drama. UY Scuti is not passive. It is a participant in the universe's endless cycle of birth, growth, death, and rebirth. In this way, it mirrors the great cycles of nature we see all around us, from the turning of the seasons to the rise and fall of civilizations. Its story is our story, written in a different script, painted on a much grander canvas. And as technology improves, telescopes grow sharper, sensors more sensitive, simulations more accurate, we will peer even deeper into the heart of UY Scuti. Perhaps we will detect subtle patterns we have missed, or witness changes in real time that provide clues to its imminent transformation. One day, perhaps in our lifetime, we may even see it explode. If we do, it will be an event unlike any other, a cosmic beacon blazing in the heavens, visible even in daylight, altering the night sky for months or years. People will look up and see a new star where none existed before, and that will be UY Scuti's final statement, a fiery farewell from a star too vast for human scale, too ancient for human memory, and yet somehow deeply connected to us all. And so, we return our gaze to UY Scuti, this celestial giant that defies ordinary comprehension. For all its grandeur and mystery, there's a stillness in its cosmic dance, a slow, lumbering pulse that mirrors the heartbeat of the galaxy itself. Though located over 9,500 light-years away, it exerts a gravitational pull, not on planets or nearby objects, but on the human imagination. It pulls scientists and stargazers alike into its story, a story that continues to evolve with each passing year. One cannot help but contemplate how such a star came to be in the first place. The origin of UY Scuti stretches back to the chaotic cradles of stellar birth, vast clouds of gas and dust known as nebulae. In one of these stellar nurseries, likely billions of years ago, gravitational instabilities caused by shockwaves from earlier supernovae may have triggered the collapse of a particularly massive pocket of matter. As gravity compressed it inward, pressure and temperature increased until nuclear fusion ignited at its core. From this moment, the clock began ticking on a short but brilliant lifespan. Unlike smaller stars, which spend most of their existence fusing hydrogen into helium in their cores through a process known as the proton-proton chain reaction, massive stars like UY Scuti quickly progress through more complex fusion processes. Once the hydrogen in the core is depleted, the star begins fusing helium into carbon and oxygen, then heavier elements like neon, magnesium, silicon, and finally iron. Each stage of this process occurs faster than the last. While hydrogen fusion can last millions of years, iron fusion is terminal. It consumes energy rather than releases it, signaling the star's inevitable collapse. UY Scuti's journey through these stages is not just rapid, it is turbulent. As it burns through fuel in concentric shells around its core, its outer layers expand and cool, giving it its red hue. This expansion is what earns it the title of a red supergiant. But the balance of outward pressure from fusion and inward pressure from gravity is delicate. Variations in fusion output, mass loss from stellar winds, and instability in its core all contribute to fluctuations in its size and brightness. Its variability is part of what makes it such an intriguing object for observation. Every flicker, every slight dimming or brightening, is a clue in a cosmic investigation. Mass loss, in particular, is an area of growing focus. Red supergiants like UY Scuti shed mass through intense stellar winds, streams of particles blown away from the star by radiation pressure and magnetic activity. Over time, this loss significantly affects the star's fate. If it loses enough mass, it may avoid a supernova and quietly transition into a white dwarf or neutron star. If not, it may explode in a cataclysmic event visible across galaxies. The precise threshold for these outcomes is still a subject of scientific debate, making UY Scuti a valuable data point in understanding stellar death pathways. Moreover, the dust and gas expelled by UY Scuti do not simply vanish into the void. They contribute to the interstellar medium, enriching it with heavier elements that serve as raw material for future star and planet formation. This recycling process is one of the most elegant features of the cosmos. Matter is neither created nor destroyed. It simply changes form, moves between states, and participates in cycles of increasing complexity. UY Scuti, by this logic, is not just a star, it is a galactic fertilizer, a cosmic gardener sowing seeds for future worlds. It's worth noting that when we look at UY Scuti, we are not seeing it as it is now, but as it was over 9,500 years ago. The light we receive today left the star long before the first pyramids were built, long before recorded history. In a way, observing distant stars is a form of time travel. We are peering into the ancient past, decoding messages that took millennia to reach us. What might UY Scuti look like now? Has it changed? Has it exploded? We simply don't know. All we have is the light it sent us in ages long gone. And yet, even in that ancient light, there are modern lessons. One of the most profound is the reminder of our scale, or lack thereof. Earth, with all its complexity, is dwarfed beyond measure by a single star in a distant region of our galaxy. And even UY Scuti, for all its magnitude, is but a grain of sand in the cosmic beach. The observable universe contains over 200 billion galaxies, each with hundreds of billions of stars. UY Scuti is extraordinary by our standards, but in the broader universe, it is one of countless actors playing a part in a drama that transcends space and time. Still, its existence invites philosophical reflection. Why should we care about a distant star? What value does it offer beyond scientific data and aesthetic beauty? The answer lies in perspective. To study UY Scuti is to confront the immensity of the cosmos. It humbles us, inspires us, and challenges us to think beyond ourselves. It shifts our focus from the temporary and the local to the eternal and the universal. It reminds us that we are part of a much larger story, one that began long before us and will continue long after we're gone. And in that realization lies a kind of peace. The universe does not revolve around us, yet we are capable of understanding it. We, tiny beings on a pale blue dot, have developed the tools to measure the size of a star nearly 1 billion times the volume of our own Sunday. We have decoded the physics of fusion, mapped the life cycle of stars, and even predicted the futures of objects we will never visit. This capacity for knowledge, for wonder, is perhaps our greatest achievement as a species. UY Scuti challenges us to continue that journey. It beckons scientists to improve our instruments, to refine our models, to dig deeper into the mechanics of stellar behavior. It encourages philosophers to ponder the meaning of scale, time, and existence. It invites storytellers and artists to capture its beauty and share it with the world. In this way, UY Scuti is not just an object of study, it is a source of inspiration, a muse in the sky that transcends disciplines and ignites the imagination. Even in the future, UY Scuti may become a symbol of human curiosity. As we advance into the era of space exploration and interstellar dreams, such stars serve as waypoints on our intellectual journey. They are beacons not only of light but of aspiration. One day, perhaps in a distant epoch, humanity, or its descendants may reach the regions of space where UY Scuti once shone. They may find its remnants, perhaps a neutron star spinning silently in the dark, or the ethereal filaments of a supernova remnant drifting through the void. And they will remember that long ago, from a small planet orbiting a modest star, beings looked up and wondered. And that act of wondering may be the most important of all. And still, the story of UY Scuti deepens, not only as an astronomical object, but as a testament to the evolving narrative of human knowledge. As we continue to scrutinize its properties through increasingly precise technologies, new questions emerge, challenging earlier assumptions and opening fresh avenues for exploration. One such area of intrigue lies in the subtle discrepancies between its observed and estimated radius. These variations can result from several complex variables, including atmospheric opacity, pulsation patterns, temperature gradients, and the difficulty of observing such distant and luminous giants. To understand the complications behind measuring the radius of a star like UY Scuti, it's essential to look into how such calculations are made in the first place. The star's angular diameter is first measured using interferometry, where light from a star is collected at different telescopes and then combined to produce higher resolution data. That angle, tiny as it is from Earth, is then combined with the estimated distance to calculate the star's true size. But here lies the challenge. Both the angular diameter and the distance are subject to error. A minor error in distance, for example, can drastically alter the estimated size of UY Scuti. If the star is actually closer or farther than originally believed, its physical radius changes accordingly. That's why the margin of uncertainty for supergiants is always large, and why some measurements initially suggested that UY Scuti was even larger than it likely is. Later recalibrations and Gaia Space Telescope data suggested a more modest size, still gargantuan by any standard, but perhaps surpassed by other red supergiants like VY Canis Majoris or Stephenson 2-18 in sheer scale. Yet the title of largest star is more fluid than fixed. The universe does not conform to human categories, and UY Scuti's radius continues to be a moving target shaped by ever-refining tools. In addition to size, UY Scuti's temperature plays a critical role in defining its classification and behavior. Its effective surface temperature is estimated to be around 3,365 Kelvin, much cooler than the Sun's roughly 5,778 Kelvin. This relatively low temperature, however, is typical for red supergiants, whose immense size compensates for their cooler nature. The cooler temperature also means that the star emits more of its light in the infrared spectrum, which is why infrared telescopes are crucial in studying such giants. Optical observations alone are often obscured by interstellar dust and gas, which scatter visible light and render distant stars faint, or even invisible in certain wavelengths. Yet that very dust and gas, often considered an obstacle to observation, tells its own story. The stellar winds from UY Scuti have cast out enormous amounts of material into the surrounding space. Over time, this outflow creates a circumstellar envelope, a vast halo of gas and dust that envelopes the star like a shroud. Observing this envelope provides insight into how massive stars lose material, and in turn, how that material seeds future generations of stars and planets. These outflows are not uniform. They are chaotic, influenced by localized magnetic fields, convection currents within the star's massive atmosphere, and even binary interactions, though UY Scuti is not currently believed to be in a binary system. These dynamics create plumes and arcs of matter that stream away from the star, eventually merging with the interstellar medium. In this way, UY Scuti participates in the grand recycling process of the galaxy. The iron in our blood, the calcium in our bones, the oxygen we breathe, all may have been forged in ancient supergiants like UY Scuti and scattered through space by stellar winds or supernovae. Indeed, the end of UY Scuti's life will be as dramatic as its current state is majestic. It is expected that UY Scuti will eventually go supernova, collapsing under its own gravity when it can no longer sustain fusion. This collapse will happen in a fraction of a second, triggering a cataclysmic explosion that will release more energy than the Sun will emit in its entire 10 billion-year life. Depending on its mass at the time of death, it may leave behind a neutron star, a hyperdense remnant roughly the size of a city, or, if massive enough, a black hole from which not even light can escape. The supernova itself will be a spectacle, one that may be visible even from Earth despite the star's great distance. It will outshine entire galaxies for weeks or months before fading, leaving behind a nebula of shocked gas expanding into space. Such events are not only visually stunning, they're scientifically invaluable. Supernovae release heavy elements into the universe, trigger new waves of star formation, and help astronomers calibrate cosmic distances. If UY Scuti goes supernova in our lifetimes, it would be one of the most studied and significant astronomical events in recent history. But there's also the possibility, albeit remote, that it may experience a quieter death. If enough mass is shed through stellar winds before the collapse, it might avoid a supernova altogether and become a massive white dwarf. This would be an unusual fate for such a large star, but not impossible. Stars often surprise us, especially those as variable and enigmatic as red supergiants. Another compelling aspect of UY Scuti is its place within the Milky Way. Located in the Scutum Centaurus arm, one of the galaxy's inner spiral arms, it resides in a densely populated region rich with other massive stars, stellar nurseries, and molecular clouds. This environment contributes to both the formation and the destruction of stars. The presence of massive stellar clusters nearby suggests that UY Scuti may have formed alongside other giants, sharing a common genesis in the collapse of a massive cloud. Yet many of its siblings have likely long since gone supernova, leaving neutron stars or black holes in their wake. UY Scuti, in its advanced age, is among the survivors of that ancient stellar cohort. The surrounding interstellar environment also influences how UY Scuti evolves. Magnetic fields, gravitational tides from nearby stars, and even pressure from surrounding gas clouds can nudge its outer layers, affect its wind patterns, and subtly alter its mass loss rate. All of these factors are studied using sophisticated models that combine real-time data with simulations, many of which are run on supercomputers. These models don't just help us understand UY Scuti, They help us build a universal framework for predicting how all massive stars live and die. As such, UY Scuti is not just an isolated curiosity. It's a cornerstone in a vast, interconnected puzzle. It informs our theories about galaxy formation, chemical enrichment, and even the origins of life itself. After all, without supernovae, there would be no elements heavier than iron, and without those elements, life as we know it could not exist. Every atom in our bodies has been through the crucible of a star, and UY Scuti is one of those crucibles, burning with the legacy of all that came before and all that will follow. And as we contemplate its enormity, we must also recognize the legacy of human endeavor that brought us this knowledge. From the first naked-eye observations of stars to the development of space telescopes, interferometers, and spectrometers, we have built a bridge to the stars, one discovery at a time. The ability to even talk about UY Scuti in such detail is a triumph of thousands of years of cumulative inquiry, built by countless astronomers, physicists, mathematicians, and engineers. Their combined efforts have given us the eyes to see across time and space, and the minds to make sense of what we find. In this way, UY Scuti is not merely a star, it is a mirror. In it we see the ambitions, the achievements, and the limitations of our species. We see a history written in light, a future unfolding in plasma and dust, and a present moment illuminated by our collective thirst for understanding. Its light, though faint to our eyes and distant from our world, serves as a beacon to the spirit of curiosity that defines humanity. UY Scuti, shimmering through the dark tapestry of space, exists in a realm beyond the grasp of our most powerful spacecraft, and yet, through the ingenuity of telescopic observation and computational modeling, we reach out across that abyss and touch its story. Every photon that leaves its surface, traveling for thousands of years before entering our instruments, carries with it a sliver of truth, a whisper of processes so immense that they escape simple comprehension. These processes are not only awe-inspiring in magnitude, they are also intricate beyond measure. The internal dynamics of UY Scuti are governed by the same fundamental laws of physics that shape our everyday world, but amplified on cosmic scales. At its core, nuclear fusion continues to drive the conversion of helium into heavier elements, releasing prodigious amounts of energy in the process. This energy pushes outward, counteracting the inexorable pull of gravity trying to collapse the star into itself. But as UY Scuti progresses through the final phases of its life, this balance becomes increasingly unstable. The layering inside the star resembles an onion, with different shells fusing different elements: helium, carbon, neon, oxygen, silicon, and so on. Each layer burns hotter and faster than the one before it, and the time frames for each stage shrink drastically. The hydrogen burning phase may last millions of years, but by the time the core starts burning silicon, the process may complete in mere days. This rapid acceleration toward catastrophe is like watching a candle flare up just before it goes out, except the flare of UY Scuti could span billions of kilometers and its end will reshape its surroundings for millennia. Throughout its life, UY Scuti has endured massive convective turbulence. Convection zones within the star churn hot plasma upward from the core and bring cooler material back down. These processes are not just background mechanics. They are essential to the star's luminosity, spectral behavior, and eventual fate. They also produce enormous star spots, cooler regions on the star's surface that can stretch across millions of kilometers. Unlike the relatively tiny sunspots on our Sun, these megastructures can drastically alter the appearance and brightness of a red supergiant. Studying them gives us rare insight into magnetic phenomena under extreme conditions. Even the outermost atmosphere of UY Scuti behaves unlike anything we are familiar with. The star's extended atmosphere is tenuous and unstable, dominated by supersonic stellar winds, shock fronts, and mass ejections. These turbulent conditions cause variability in the star's brightness, leading to its classification as a semi-regular variable star. Such variability isn't merely an observational inconvenience, it's a clue to the pulsations and instabilities brewing beneath the surface. These pulsations, which stretch and compress the star in slow, rhythmic cycles, are vital for understanding the transfer of energy and mass in late-stage stellar evolution. And here lies one of the most fascinating and humbling aspects of UY Scuti. its impermanence. For all its grandeur, it is in a state of terminal decline. The mass it sheds today is evidence of a core growing ever closer to collapse. That core, when it finally fails to sustain fusion, will experience an implosion that triggers the famed supernova. In this final act, the elements forged over millions of years will be expelled at nearly a tenth the speed of light, enriching the interstellar medium with the seeds of new worlds. Some of those elements, iron, gold, uranium, require the extreme conditions of such an explosion to form. They will drift through the galaxy for eons, and one day, perhaps, coalesce into new stars, new planets, and even new life. Thus, UY Scuti is not only ending, it is giving. Its death will become the beginning of countless other stories, some of which may never be written, and others that may, one day, evolve to look up at the stars and wonder about their origins. And what of its immediate legacy? The shockwave from its explosion will race outward, interacting with the remnants of its own stellar wind and dust envelope. This collision will generate new nebulae, structures of surreal beauty and scientific interest. The supernova remnant, though chaotic, will provide astronomers with valuable data about the composition of the progenitor star, the dynamics of explosion, and the geometry of the resulting ejecta. This makes UY Scuti a natural laboratory, a subject for models and simulations that attempt to predict not only what will happen when it dies, but also what happens to the surrounding galaxy in response. The gravitational perturbations alone could ripple through nearby clusters, subtly reshaping orbits and triggering new star formation events. These indirect consequences, while difficult to trace, form part of the vast web of causality in which every star is a node and every death is a turning point. Even now, as it lives out its final epochs, UY Scuti continues to influence the region around it. Its powerful winds shape clouds of interstellar gas, its radiation ionizes nearby atoms, and its presence disturbs gravitational balances in local clusters. Observing this in real time is akin to witnessing a glacier carving a mountain range, an awe-inspiring reminder of the slow, inevitable artistry of nature on the grandest scale. And yet, despite all this grandeur, we must acknowledge a strange truth: UY Scuti may not be unique. There may be stars out there, in our galaxy or beyond, that are even larger, more luminous, or more massive. The universe is vast beyond imagining, and our catalog of stars is far from complete. New discoveries are made regularly, and the title of largest known star has changed hands many times before and will likely do so again. What sets UY Scuti apart is not only its current claim to fame, but its ability to serve as a symbol, a monument to our ambition to understand the incomprehensible. We look at UY Scuti and see more than just a star. We see a relic of cosmic history, a participant in the ongoing story of galactic evolution, and a preview of stellar futures. We also see our own reflections, our desire to comprehend our place in the universe, to measure the immeasurable, and to find meaning in the patterns written across the heavens. The instruments we use to study UY Scuti, interferometers, spectroscopes, photometers, are not just tools, they are extensions of human curiosity. They allow us to translate light into knowledge, distance into understanding, and time into legacy. Every data point recorded, every simulation rendered, brings us closer to the truth, even as the universe continues to evolve and surprise us. In this endless pursuit, UY Scuti stands as a milestone. It challenges us with its complexity, awes us with its scale, and inspires us with its story. It reminds us that even in the face of cosmic enormity, the human mind can reach outward and make sense of the stars. The light from UY Scuti is ancient. The photons that strike our telescopes today began their journey thousands of years ago, long before the dawn of recorded human history. They traveled unimpeded through the void, passing stellar debris, dark nebulae, and uncharted regions of our galaxy to finally meet our lenses, our sensors, our eyes. In this way, UY Scuti is not just a star, it is a time capsule, a frozen moment from an epoch when civilizations on Earth had not yet dreamed of the stars. And this delay in light is not just poetic, it is profoundly important to astrophysics. It means that everything we observe is history. The immense distance of UY Scuti places us in the position of cosmic archaeologists, piecing together past events from light that has journeyed for millennia. Even if UY Scuti had already gone supernova, we would not know for a very long time. The image we see now is a portrait of the past, one that cannot be updated until nature allows it. Its light is a kind of stellar testimony, one that informs us about surface temperature, chemical composition, and velocity through the Doppler effect. Every tiny fluctuation, every faint line in the spectrum, holds a wealth of secrets. It's how we know that UY Scuti is rich in elements like hydrogen and helium but also contains traces of heavier elements, carbon, oxygen, magnesium, formed deep within its core. These elements absorb and emit light at specific wavelengths, creating identifiable spectral lines that function like a fingerprint. By analyzing those fingerprints, we've come to learn that UY Scuti is a relatively cool star, hovering around 3000 to 3500 Kelvin on the surface. This temperature, while blistering by earthly standards, places it squarely in the category of red supergiants, stars in their twilight, having exhausted the hydrogen that once powered their youthful brilliance. This low temperature gives UY Scuti its red-orange hue and accounts for its expanded, diffuse outer layers. This temperature also tells us something about its life expectancy. Unlike smaller stars like our Sun, which burn hydrogen slowly and live for billions of years, massive stars like UY Scuti race through their lives. The larger the star, the faster it burns its fuel. UY Scuti, with a mass more than 30 times that of the Sun and a radius that dwarfs the orbit of Jupiter, is living life in the fast lane. Its remaining lifespan is likely measured in hundreds of thousands of years, perhaps even less. The internal structure of UY Scuti is not just massive, but turbulent. The core is the site of advanced nuclear fusion reactions, where elements heavier than hydrogen are built up under enormous pressure. The process of stellar nucleosynthesis continues layer by layer, hydrogen fusing into helium, helium into carbon, carbon into neon, neon into oxygen, and so on. Each fusion stage takes place in a different shell around the core, creating a stratified structure of incredible complexity. This cascade of fusion reactions is driven by the need to maintain equilibrium between gravity and radiation pressure. Gravity seeks to pull the star inward, collapsing it under its own immense weight. Radiation, produced by nuclear fusion, pushes outward. As long as these two forces are balanced, the star remains stable. But that balance is precarious. When the fusion process reaches iron, the energy balance collapses. Iron does not yield energy when fused, so the star's core can no longer resist gravity. That's when the real fireworks begin. The collapse of the core is almost instantaneous, occurring in fractions of a second. Gravity takes over, crushing the core into a superdense object, possibly a neutron star or black hole, depending on the star's final mass. At the same time, the outer layers are violently expelled into space in a cataclysmic supernova explosion. This explosion can outshine entire galaxies for days or weeks, releasing more energy in that short time than our Sun will produce in its entire life. When UY Scuti finally reaches that point, it will leave behind a stellar remnant and a cloud of expanding gas and dust known as a supernova remnant. These remnants are rich with heavy elements, gold, silver, platinum, that are formed only in the extreme conditions of supernova nucleosynthesis. These elements will be ejected into the interstellar medium, contributing to the formation of new stars, new planets, and potentially, new life. In this way, UY Scuti will not end, it will transform. It will become part of something new, a participant in the eternal cycle of cosmic creation and destruction. It will return its substance to the galaxy, and in doing so, extend its influence far beyond the limits of its own light. But before that final act, UY Scuti continues to fascinate us in its present state. Its sheer size challenges our understanding of stellar physics. The Sun, immense as it is, could be swallowed hundreds of millions of times by UY Scuti's volume. Even Saturn's orbit might lie within the bounds of this stellar colossus. Such dimensions strain the mind and the models we use to simulate them. How can a star remain gravitationally bound when its outer layers are so diffuse, so tenuous, so spread out across space? The answer lies in the extremely low density of the outer layers. Despite its size, UY Scuti is not especially dense. In fact, Most of its mass is concentrated near the core, with the outer layers resembling a vast, hot fog of plasma and gas. These regions are so thin that a spacecraft passing through them might not even register a collision with a single atom for miles. It is this low density that allows the star to expand to such a gargantuan scale without tearing itself apart. It also makes UY Scuti incredibly delicate. Small fluctuations in pressure, temperature, or fusion rate can ripple outward and cause massive changes in brightness, shape, and mass loss. The star constantly sheds material through solar winds and massive ejections, contributing to a halo of dust and gas that surrounds it like a shroud. This halo makes direct observation difficult, and one of the reasons our estimates of UY Scuti's size vary is due to the opacity of this circumstellar material. Despite these challenges, astronomers use a variety of techniques to refine their models of the star. Infrared imaging helps pierce through the dust, while spectroscopic analysis reveals chemical composition and surface velocity. Interferometry, the process of combining light from multiple telescopes to achieve higher resolution, has been particularly useful in resolving the star's disk and measuring its diameter with more precision. These methods continue to evolve. As our tools improve, so too will our understanding of UY Scuti and other supergiants like it. The James Webb Space Telescope, launched with the purpose of peering into the early universe and the dustiest regions of the galaxy, may offer fresh insights into the life cycles of stars like UY Scuti. It can detect infrared radiation that escapes even the thickest clouds of dust, allowing us to probe deeper into the hearts of stellar giants. Meanwhile, ground-based observatories continue to monitor UY Scuti for changes in brightness and structure. This monitoring is crucial for predicting the star's future. The timing of a supernova is incredibly hard to pinpoint, but certain signs, changes in pulsation period, sudden drops or spikes in brightness, increased mass ejection, could serve as precursors. One day, perhaps within our lifetimes, astronomers may sound the alert: UY Scuti has entered its final phase. Until then, the star continues its majestic burn, casting its crimson light across the cosmos. It remains both a mystery and a monument, an emblem of cosmic scale and a mirror of our own impermanence. For every moment it exists, it reminds us that even the largest things in the universe are subject to change, decay, and rebirth. As the pulsating heart of UY Scuti continues to emit its slow, rhythmic beats across the void, scientists are ever more captivated by the phenomena that unfold within and around it. The star's variability in brightness, its identity as a pulsating variable, is a profound clue to its internal workings. Unlike the more stable glow of our Sun, UY Scuti's light curve changes over time, expanding and contracting like a living, breathing organism. These fluctuations are not random. They are deeply tied to the star's internal pressure, gravity, and fusion processes, acting like signals in the deep, cosmic night. The mechanism behind this variability is called radial pulsation. The outer layers of UY Scuti expand and cool, causing a dip in brightness, and then contract and heat, leading to a rise in luminosity. This cycle repeats over a relatively stable period, about 740 days for UY Scuti, each pulse a heartbeat in its dying rhythm. These pulsations, though gentle on a human timescale, involve the movement of material across distances equivalent to multiple Earths. Imagine an ocean of incandescent gas flowing outward for millions of kilometers, only to be pulled back again by gravity's insatiable grip. It's a dance of destruction and renewal happening constantly, invisibly, at a scale that our minds strain to grasp. Understanding these pulsations isn't just for the sake of curiosity, it's fundamental to astrophysics. By analyzing the pulsation period, astronomers can derive insights into the star's mass, density, and internal structure. This is akin to listening to the rumble of an engine to diagnose its condition. Every oscillation, every flicker of brightness, is a message from the star's innards. In the case of UY Scuti, this has helped confirm that it has entered the late red supergiant phase of its life, an evolutionary point from which there is no turning back. But let's step back and place UY Scuti in the larger context of stellar evolution. Stars like UY Scuti begin their lives in massive clouds of gas and dust, nebulae. Gravity causes regions of these clouds to collapse, forming a protostar. As the protostar accretes more material, pressure and temperature at its core increase until hydrogen fusion begins. This marks the birth of a star. For massive stars, this main sequence phase is relatively short-lived. They quickly burn through their hydrogen fuel and begin fusing heavier elements. UY Scuti, having long since left the main sequence, is now in a transitional state. It is burning helium and possibly heavier elements in shells around an inert core. This layered structure resembles an onion, each layer producing different fusion reactions, releasing energy and contributing to the star's outward pressure. But this configuration is unstable. As the core grows heavier and denser, the star's internal equilibrium becomes more precarious. The outer layers puff outward in response to the energy produced inside, leading to the bloated, diffuse structure we observe. The life of UY Scuti is thus governed by the constant struggle between gravity and radiation pressure. And though radiation has the upper hand for now, gravity is patient. It waits for the moment when fusion can no longer produce enough energy to support the star's mass. When that moment comes, gravity will act decisively, causing the core to collapse in milliseconds, triggering a supernova that could be visible from Earth even during daylight. This eventual explosion will not only be a spectacle, it will be a scientific bonanza. Supernovae are among the most important events in the cosmos. They enrich the interstellar medium with heavy elements, trigger the formation of new stars, and help calibrate distances across the universe through Type II supernova light curves. If we were to witness UY Scuti's death in our lifetime, it would be one of the most studied and documented events in modern astronomy. Data would be collected across the electromagnetic spectrum, from X-rays to radio waves, giving us an unparalleled view into the death throes of a red supergiant. But before we reach that finale, there is still much to explore about UY Scuti in its current form. One of the more curious aspects of its immense size is the effect of convection. The outer layers of the star are not static. They are constantly churning with convective currents, similar to boiling water but on a scale that dwarfs entire planets. Hot gas rises to the surface, cools, and sinks again, creating massive convective cells that can span tens of millions of kilometers. These cells are so large and dynamic that they contribute to irregularities in the star's brightness and shape. Some astronomers speculate that these convective patterns might cause localized mass ejections, giant plumes of gas that rise and escape the star's gravity. These mass loss events are significant because they gradually strip away the star's envelope, altering its evolution and shortening its lifespan. Over time, UY Scuti may shed enough mass to shift its fate. If it loses enough material, it might avoid collapsing into a black hole and instead become a neutron star. However, this is uncertain. Stellar evolution at these scales is influenced by chaotic and often unpredictable processes. Another factor to consider is rotation. Most stars spin, and while red supergiants like UY Scuti tend to rotate slowly due to their expansion, even a modest rotational speed can have effects on the star's shape and mass distribution. Rotation can cause the star to bulge at the equator, altering its surface gravity and affecting how material is lost over time. Moreover, rotation can influence magnetic fields, which in turn play a role in shaping stellar winds and mass ejection patterns. UY Scuti's magnetic field is likely weak compared to smaller, more compact stars, but even a weak field on such a massive scale can have outsized effects. It may help channel material into bipolar outflows or contribute to the formation of circumstellar structures like disks and shells. These structures are often observed around other massive stars and serve as evidence of ongoing mass loss and magnetic shaping. As we continue to study UY Scuti, we also learn more about the broader class of red supergiants. These stars, including Betelgeuse and VY Canis Majoris, exhibit similar characteristics and evolutionary pathways. By comparing them, astronomers can identify common features and isolate unique ones. This comparative analysis deepens our understanding of stellar physics, providing templates for modeling stellar death and supernova mechanics. For instance, Betelgeuse has recently shown dramatic dimming events, sparking global interest in its potential to go supernova. These events turned out to be caused by dust clouds and convective changes, but they offered a glimpse into the complexity of red supergiants. UY Scuti, with its even more extreme size, offers a more exaggerated version of these dynamics, allowing us to study processes that are otherwise too subtle to detect. And beyond the individual star, UY Scuti plays a role in the ecology of the galaxy. Massive stars like it are the engines of galactic evolution. They stir the interstellar medium, enrich it with elements, and initiate waves of star formation through their winds and eventual deaths. Their radiation sculpts nebulae, their remnants seed new worlds. In this grand tapestry, UY Scuti is not an isolated marvel. It is a key participant in a cosmic cycle that includes stars, planets, and potentially life itself. Its future is uncertain, but that uncertainty is precisely what makes it exciting. UY Scuti might live out the next few 100,000 years in relative peace, shedding mass and fading slowly. Or it might collapse in a dramatic supernova tomorrow, leaving astronomers scrambling to record every photon of the event. Either way, it reminds us of the fragility of even the mightiest structures in the universe. It reminds us that size is no guarantee of permanence, and that even the most colossal beings eventually meet their end. And so, UY Scuti hangs in the sky, barely visible to the naked eye yet vast beyond comprehension. It is a silent monument to the power of gravity and fusion, a red colossus on the brink of oblivion. It speaks to us not in words, but in wavelengths and oscillations, in heat and dust and light. To look upon it, even through data, is to feel small, but also connected to something unimaginably grand. And yet, as the celestial behemoth looms across the distant reaches of our Milky Way, the human imagination continues to be stirred by UY Scuti's very existence. Its sheer size defies ordinary comprehension. If placed at the center of our solar system, its outer surface would reach beyond the orbit of Jupiter, possibly even further depending on the current estimate of its radius. This thought alone places it among the most humbling objects we know in the cosmos, for it dwarfs not only Earth, but even our understanding of what it means to be large. When astronomers speak of UY Scuti's estimated radius, roughly 1,700 times that of the Sun, they are referring to an approximation, shaped by both observational limitations and the nature of the star itself. Red supergiants are notoriously hard to measure precisely, as their boundaries are not as clearly defined as those of smaller stars. Their outer atmospheres are diffuse, translucent, and ever-changing due to the internal dynamics of convection and mass loss. A more precise term might be apparent radius, for what we observe is more of a fluctuating shell of radiating plasma rather than a clean stellar surface. Even so, the staggering numbers are real. The estimated volume of UY Scuti is so immense that it could fit more than 5 billion suns inside. That's not a poetic exaggeration, that's an astrophysical reality. And yet, despite this tremendous bulk, its mass is only about 30 times that of the Sun. This points to its extremely low average density, with its outer layers so expanded and tenuous that a spacecraft could theoretically fly through large parts of it with minimal resistance, as if passing through a fog of incandescent gas. This aspect of low density, paired with extreme luminosity, presents a paradox of sorts. UY Scuti emits roughly 340,000 times more energy than the Sun, a truly colossal output. But because of its surface area, its surface temperature is relatively cool, estimated at around 3,365 Kelvin. By comparison, the Sun's surface temperature is around 5,778 Kelvin. This cooler temperature explains its deep red hue, visible in spectral data and responsible for its classification as a red supergiant. Color in stars is directly related to temperature, and UY Scuti radiates in the lower energy red and infrared parts of the electromagnetic spectrum. What's fascinating here is that temperature, luminosity, radius, and mass all interlink through the laws of stellar physics. The Stefan-Boltzmann law, for instance, helps astronomers calculate a star's luminosity based on its temperature and radius. With UY Scuti's known temperature and brightness, researchers back-calculate its radius, which, although still subject to error margins, consistently places it among the largest known stars by radius. Still, UY Scuti is not the most massive star. That title goes to stars like our 136A1, a Wolf-Rayet star in the Large Magellanic Cloud, which is estimated to have more than 150 times the mass of the Sun. Nor is it the most luminous star. Others, like Eta Carinae, put out even more energy. But in terms of sheer physical girth, of volume, of spatial domination, UY Scuti stands near or at the top. This distinction makes it a useful case study in how stars of extreme size can exist without the highest mass, and how their life paths diverge from those of their more compact but more massive cousins. Understanding how UY Scuti reached this size is critical to understanding the limits of stellar evolution. Its current state reflects a delicate balance of forces: radiation pushing outward, gravity pulling inward, and mass loss acting like a release valve to slow its march toward collapse. But make no mistake, collapse is coming. Like all massive stars, UY Scuti is destined to die in one of the universe's most violent cataclysms, a supernova. The timing, though, remains a mystery. It could happen in a few 100,000 years, a blink of an eye in cosmic time. Or, due to uncertainties in its mass loss rate and internal structure, the end could come sooner. Astronomers are now equipped with sophisticated tools: space-based telescopes, radio observatories, interferometry arrays, to monitor such stars continuously. Infrared observations, in particular, are crucial because stars like UY Scuti often shroud themselves in thick clouds of dust, created from expelled gas cooling and condensing in space. This dust plays an essential role in galactic ecology. It becomes the raw material for future stars, planets, comets, and possibly life. Thus, even in its twilight, UY Scuti is a giver, a creator of matter that might one day coalesce into a world of oceans and skies. That idea alone expands our emotional connection to such stars. They are not merely remote and distant. They are the ancestors of all that is solid, all that breathes. Yet while we understand many aspects of UY Scuti's current state, the star still hides secrets. One such mystery involves its internal rotation. Given the size of the star, measuring rotation is difficult. However, even slow rotational speeds can create instabilities and asymmetries in the star's structure. Over long timescales, this rotation could contribute to uneven mass ejection, creating features like lobes, arcs, and bipolar outflows. In some cases, rotation might help explain why certain supernovae explode more violently or asymmetrically than others. Another field of interest is the magnetic environment surrounding UY Scuti. While large stars usually have weaker surface magnetic fields, any field present can have dramatic effects due to the massive scale. Magnetic fields can shape stellar winds, carve out cavities in surrounding space, and potentially influence how a star collapses. The exact mechanism by which such fields interact with UY Scuti's outer envelope is still a topic of research, especially as we discover more about magnetically active giants across the galaxy. And what about companions? Binary star systems are common in our galaxy. Perhaps the majority of all stars exist in multi-star systems. If UY Scuti has a stellar companion, that relationship could deeply affect its mass loss history and future supernova profile. A companion star could siphon material from UY Scuti or be influenced by its gravitational presence in a way that creates eccentric orbits and powerful tidal forces. So far, no confirmed companion has been identified for UY Scuti, but ongoing monitoring might yet reveal subtle clues, variations in radial velocity or distortions in spectral lines. When the final moment comes, UY Scuti's death will likely be a Type 2P supernova, a class marked by a sharp peak in brightness followed by a long, plateau-like decline. This plateau results from hydrogen recombination in the ejected material. It will be a brief but glorious finale, shining with the combined brilliance of billions of suns. And afterward, what remains? If the mass of its core exceeds the Tolman, Oppenheimer, Volkoff limit, the remnant will collapse into a black hole, warping spacetime and becoming invisible save for its gravitational echo. Otherwise, it might become a neutron star, a city-sized sphere of degenerate matter spinning at unfathomable speeds. The debris field of such a supernova will stretch across light years, becoming a supernova remnant glowing in X-rays and radio waves. It will join the ranks of cosmic sculptures like the Crab Nebula, chaotic, luminous clouds bearing witness to the explosive end of a massive star. These remnants persist for tens of thousands of years, gradually cooling and enriching the interstellar medium with heavy elements like gold, platinum, uranium, and more. Every atom of calcium in your bones and every molecule of iron in your blood likely came from such an event. That's not poetry, that's astrophysics. And UY Scuti, by virtue of its mass and age, is poised to become the source of such material. When it dies, it will not vanish. It will transform. It will give birth to new worlds. UY Scuti's eventual demise, though millions of years away, underscores its place in the greater cosmic cycle. The elements released during the final supernova will be mixed into the interstellar medium, enriching it with heavier elements that are critical for the formation of planets, life, and even the stars that will follow. While UY Scuti may seem like an extraordinary anomaly to us, in the grand scope of galactic history, it is just another chapter in a story of continuous rebirth. When we look at UY Scuti, we are not just observing a distant star in isolation. We are witnessing a dynamic, ongoing process that has occurred throughout the universe's 13.8 billion year history, where every generation of stars creates the conditions for the next. And though UY Scuti may have taken its first breath as a massive molecular cloud of gas, over time it has grown, expanded, and matured into one of the largest known stars. The death of UY Scuti will similarly give birth to new conditions for life and formation. Such stars are cosmic factories, and their explosions represent the kind of natural cycles that drive the evolution of the universe. In some ways, UY Scuti is a metaphor for the universe itself, expansive, turbulent, and on a relentless march toward eventual transformation. In the final moments of its life, as its core collapses and it reaches the precipice of a catastrophic collapse, we will be reminded of the vastness and the complexity of stellar evolution. We, on Earth, are on a tiny speck of dust in the vastness of space, yet every star, from the most minute to the most enormous like UY Scuti, plays an integral part in shaping the universe and the conditions for life. There is something uniquely poetic about the fact that UY Scuti, a star so far removed from our everyday experiences, is responsible for the very elements that make up our existence. The iron in our blood, the calcium in our bones, and the oxygen that fills our lungs are all remnants of ancient stars, some of which, like UY Scuti, went through a violent and transformative death to create the universe's most essential building blocks. Looking back in time, stars like UY Scuti may have once been born from the remnants of other supernovae, collapsing gas and dust that once formed stellar nurseries. Over millions of years, gravitational forces would have caused the gas to collapse, triggering nuclear fusion at the core and lighting the birth of yet another stellar giant. These stars would burn brightly, growing in size and luminosity until they reached a point where they could no longer sustain themselves. One of the most fascinating things about UY Scuti, and stars like it, is the fact that they are caught in a constant battle between the internal forces of gravity and radiation. Gravity pulls inward, trying to collapse the star, while the outward pressure of nuclear fusion pushes outward, preventing that collapse. Over time, as a star like UY Scuti burns through its fuel, the balance between these forces begins to falter. This imbalance triggers a series of events that will eventually lead to the star's expansion into the massive red supergiant we observe today. As the fuel in the core begins to run out, the fusion process slows down, and the core starts to contract. This contraction heats up the core, which triggers the fusion of heavier elements, like helium and carbon. As this happens, the outer layers of the star expand, increasing its size dramatically. This expansion into the red supergiant phase is what makes UY Scuti one of the largest stars known. Its size comes not from its mass, but from the fact that it has run out of fuel for its core fusion process and is now undergoing a series of complex changes that cause its outer layers to puff up. This shift in the star's behavior doesn't happen in isolation. It's part of a natural progression of stellar evolution that all massive stars undergo. Stars like UY Scuti begin life with massive amounts of hydrogen in their cores, which they fuse into helium. This process generates vast amounts of energy, allowing the star to shine brightly for millions of years. But as the hydrogen is consumed, the core begins to collapse, and this leads to the fusion of heavier elements. As the star ages, its size and luminosity grow, eventually transforming into a red supergiant, a phase that can last anywhere from hundreds of thousands to a few million years. The lifespan of a star like UY Scuti is a brief one, compared to smaller stars like our Sun. The larger the star, the shorter its life, because the rate of fusion in its core is much higher. This rapid fusion leads to an accelerated consumption of fuel, causing the star to burn through its resources much faster. As a result, the life of a massive star is a rapid, intense process, characterized by dramatic changes and explosive events that can reshape the entire galaxy. And though the end of UY Scuti may seem far off in the future, its death will play a key role in the cosmic landscape. Supernovae are some of the most energetic and spectacular events in the universe. They release vast amounts of energy, enough to outshine entire galaxies for a brief period. In doing so, they are not just an end, but a beginning, a source of energy and material that will seed the formation of new stars, planets, and even life forms. Once UY Scuti explodes, the shockwave from the supernova will propagate through the surrounding space, compressing gas and dust in nearby regions and triggering the formation of new stars. The heavy elements that are synthesized during the explosion, elements like gold, uranium, and platinum, will be scattered across the universe, enriching the interstellar medium and giving rise to the formation of new planetary systems. In this way, the death of one star leads to the birth of countless others, continuing the cycle of creation and destruction that defines the life of the universe. This incredible process, which is repeated in stars across the cosmos, underscores the interconnectedness of all things in the universe. Even the smallest, most mundane objects, like the air we breathe or the ground beneath our feet, are linked to these vast, cosmic cycles. The same elements that make up UY Scuti, the Sun, and our own bodies are part of a continuous flow of matter and energy that stretches back to the earliest moments of the universe. Ultimately, what we observe in UY Scuti is a reminder of the ephemeral nature of the universe. Stars, even the most massive ones, are not eternal. They burn brightly for a time, and then they fade, leaving behind a legacy that can shape the future. And while the star itself may eventually die, the elements it produced will continue to live on, passing through new generations of stars and planets, and perhaps even new forms of life. The story of UY Scuti is one that exemplifies the cyclical nature of life and death in the cosmos. While it is true that we are observing a star that is far from our reach, the effects of its existence reverberate through the fabric of the universe. Every element, every photon emitted, every burst of radiation that emanates from this colossal giant, contributes to a web of cosmic interconnection that is beyond our full understanding. When we think of UY Scuti, we're not just observing the present state of a star, but a snapshot in time, capturing a brief moment in the long arc of stellar evolution. From its birth to its explosive demise, UY Scuti's life is a journey of unimaginable scale. Its story is part of the very fabric of the universe itself, a story that is constantly unfolding, where stars, galaxies, and the elements that make life possible are in constant flux. It serves as a reminder that everything, no matter how grand or minuscule, is part of an interconnected, ever-evolving process. As we zoom out and observe UY Scuti's role in the universe, we realize that this star is not unique in its vastness, but rather an example of a broader trend among the largest stars. Supergiants like UY Scuti, while awe-inspiring and visually stunning, are only one chapter in the grander story of stellar evolution. There are other giants, each with its own history, composition, and eventual fate. And while UY Scuti is one of the largest by radius, there are other contenders, each with their own distinct characteristics that make them fascinating in their own right. Stars like VY Canis Majoris and VY Sagittarii, though slightly smaller in size, still dwarf our Sun by enormous margins, demonstrating the diversity of these celestial objects. The study of stars like UY Scuti not only enhances our understanding of the life cycles of massive stars, but also sheds light on the larger processes that shape galaxies. The remnants of stars, whether they form black holes, neutron stars, or simply fade into nothingness, contribute to the overall structure of the universe. The heavy elements released by stars like UY Scuti during their death throes are essential ingredients for life and the formation of planets. Without supernovae and the process of stellar death, the universe would be a far less complex place, devoid of the materials needed to create the diversity of worlds we see today. In fact, the very planet on which we stand is a product of these processes. Earth, like the rest of the solar system, is made up of elements forged in the cores of long-dead stars. The heavy elements, carbon, oxygen, nitrogen, and iron, are products of stellar nucleosynthesis. In simpler terms, the atoms that make up our bodies, the air we breathe, and the world we walk on were once part of stars that lived, died, and exploded. These explosions spread those elements far and wide, seeding the formation of new stars and planets. It's a cosmic recycling process that has been happening for billions of years, and it continues to this day. The death of stars like UY Scuti does not just provide us with the elements we need for life, it also contributes to the formation of new stars. The shockwaves produced by a supernova can compress surrounding gas and dust, initiating the process of star formation. As the interstellar medium is disturbed by the explosion, clumps of gas begin to collapse under their own gravity, forming new stars. This process has been happening for as long as stars have existed, creating a cycle of birth and death that keeps the universe in constant motion. Beyond their role in enriching the interstellar medium and providing the building blocks for new stars, massive stars like UY Scuti also influence their surroundings in other profound ways. The immense radiation produced by stars of this size can have a significant impact on the surrounding gas and dust. This radiation can ionize nearby gas, causing it to glow in various wavelengths, and it can also affect the formation of planets. In some cases, the intense radiation and stellar wind from a nearby supergiant can even strip away the atmospheres of nearby planets, rendering them inhospitable to life. On a galactic scale, stars like UY Scuti are also important for the dynamics of their host galaxies. Their gravity can affect the motion of nearby stars and gas, and their intense radiation can shape the overall structure of their galactic neighborhoods. In a sense, these giant stars are the engines that drive the evolution of galaxies, creating the conditions for the formation of new stars, new systems, and new planets. In this sense, stars like UY Scuti are not just massive objects to be admired from afar. They are active participants in the grand narrative of the universe. Their lives are intricately woven into the broader patterns of galactic evolution, and their deaths mark the beginning of new cycles of creation and destruction. The story of UY Scuti is one of growth, expansion, and eventual decay, but it is also a story of regeneration and rebirth. The study of UY Scuti and other supergiant stars helps us to understand the processes that govern the lives of all stars. From the smallest red dwarf to the most massive blue giant, stars are governed by the same basic principles of physics. The balance between gravity and radiation, the fusion of elements in their cores, and the eventual collapse of their cores as they run out of fuel. All of these processes are part of the natural life cycle of a star. And while UY Scuti may be one of the largest and most dramatic examples of this cycle, it is far from the only one. In the future, as we continue to refine our tools and techniques for observing distant stars, we will likely discover even larger and more massive stars than UY Scuti. The search for these giants will reveal more about the extremes of stellar evolution and the forces that govern the universe. We may also discover new insights into the behavior of stars, the formation of galaxies, and the nature of the universe itself. For now, however, UY Scuti stands as one of the largest and most awe-inspiring stars we know. Its enormous size, radiant luminosity, and eventual transformation into a supernova are a testament to the immense power and complexity of the universe. As we look up at the night sky and gaze upon the stars, we are reminded that these distant, fiery giants are not just points of light. They are the lifeblood of the cosmos, fueling the creation and destruction of everything we know. The cycle of birth, life, and death in stars is a process that takes millions to billions of years, but every stage of a star's existence plays a crucial role in shaping the universe. Stars like UY Scuti, which are massive and luminous, leave a lasting legacy through the way they influence the surrounding interstellar medium. The vast energy produced by these stars accelerates the life cycle of their host galaxies, triggering the formation of new stars, planets, and even triggering cosmic phenomena like gamma-ray bursts and supernovae. As these massive stars live out their short but intense lives, they paint a picture of the universe's expansive potential, a universe filled with wonder and processes that remain an enduring mystery to humanity. There is something inherently fascinating about the life of UY Scuti that captivates the imagination. As one of the largest stars known by radius, it serves as a reminder of the limits of our own perceptions and comprehension of the cosmos. We are in awe not only of its sheer size but also of the thought that such a massive body, glowing brightly in the cosmic night, is merely a phase in a far larger process of stellar evolution. The death of UY Scuti, whether it ends as a black hole or a neutron star, will mark the end of an era in the timeline of the universe. Yet, in that death, a new beginning will emerge, contributing to the cosmic recycling of elements, fueling the formation of new stars, and even potentially giving rise to planets that could harbor life in distant future epochs. Stars like UY Scuti play a significant role in the larger cosmic story. Without their immense power and catalytic influence on the interstellar medium, the elements that make up everything from stars to galaxies, planets, and even life itself, would never have been distributed throughout the universe. Supernova explosions, which often mark the death of stars like UY Scuti, are among the most energetic events in the universe, creating the heavy elements, such as iron, gold, and uranium, that are essential for the formation of planets and life. These elements are spread out into space, enriching the gas clouds that give birth to new stars and solar systems. But the life and death of UY Scuti are not the only significant factors that make it an interesting object of study. It is also part of the broader category of red supergiants, massive stars that have expanded to a size far greater than that of our Sun. These stars exist in a delicate balance between gravity and pressure. Gravity pulls inward, and the pressure from nuclear fusion in their cores pushes outward. As the star's core runs out of fuel, this balance shifts, and the star expands dramatically. This expansion is not without consequences. The outer layers of red supergiants like UY Scuti are not as tightly bound to the core, making them incredibly vulnerable to even the smallest disturbances. Any significant change in the star's internal balance could cause the outer layers to be expelled in a catastrophic explosion, a supernova. UY Scuti's immense size, coupled with its evolutionary phase, brings to light many questions about the nature of the universe. How do these stars grow so large? Why do they end their lives in such violent explosions? And what does their death mean for the universe as a whole? These questions drive much of our current scientific investigation into the lives of the most massive stars in the universe. But as much as we know, there is still so much we do not yet understand. For instance, the exact mechanisms behind the expansion of red supergiants are still the subject of ongoing research. Scientists are investigating how these stars manage to expand to such enormous sizes while maintaining their overall structure. How do their cores manage to produce the energy needed to sustain their growth? And what happens when their cores run out of fuel? At what point does the pressure from fusion in the core become so great that the star's outer layers are cast off, leaving behind a dense remnant, either a white dwarf, neutron star, or black hole? These questions, which extend to stars like UY Scuti and other massive red supergiants, highlight the immense complexity of stellar evolution. Stars don't simply burn bright and fade away in an orderly fashion. Instead, their lives are filled with dramatic fluctuations and events that challenge our understanding of physics. Understanding these massive stars, how they form, how they evolve, and how they die is crucial not only for understanding the life cycles of stars but also for understanding the forces that shape the universe itself. Moreover, while UY Scuti is among the largest stars known by radius, its story is still being written. With each new observation, astronomers and astrophysicists continue to refine our understanding of its properties, adding new details to its story. For instance, the measurement of its precise size has changed over time, as new technologies allow for more accurate observations. Early estimates put UY Scuti's radius at an astonishing 1,700 times that of our Sun, but more recent measurements suggest that it may be somewhat smaller, though still massive by any standard. Despite the challenges in measuring such a far-off star, what is clear is that UY Scuti is one of the most extreme examples of a red supergiant in the universe. Its sheer size, its luminosity, and its place in the cycle of stellar evolution serve as a testament to the complexity and wonder of the cosmos. It is an object of intense scientific interest, and it continues to inspire researchers and stargazers alike. As we look toward the future of space exploration, the study of stars like UY Scuti will only become more important. New telescopes and technologies will allow us to peer deeper into space, revealing more about the lives of these colossal stars. These observations could lead to breakthroughs in our understanding of stellar physics, as well as our understanding of the universe as a whole. By studying these stars, we can learn not only about the stars themselves but also about the broader processes that shape the galaxies, the elements that make up planets, and the conditions necessary for life to exist. UY Scuti represents more than just a large star. It represents the scale and complexity of the universe itself. From its incredible size to its eventual fate, UY Scuti tells a story of cosmic growth, death, and rebirth. It reminds us that the universe is filled with extraordinary phenomena that challenge our perceptions of what is possible. As we continue to explore and learn about stars like UY Scuti, we are not only deepening our understanding of the cosmos but also learning more about the forces that shape our own existence. Stars like UY Scuti are not just distant objects in the sky, they are the building blocks of the universe, and their study helps us unlock the mysteries of the universe and our place within it. The study of stars like UY Scuti is not just about measuring size or calculating mass. It's about understanding the intricate processes that drive the evolution of these stars and the profound impact they have on their surroundings. Every detail of UY Scuti's life, from its formation in the molecular clouds of gas and dust to its eventual demise in a cataclysmic supernova, is a glimpse into the workings of the universe itself. The sheer enormity of UY Scuti's size forces us to think on scales beyond what we experience in our everyday lives. The Sun, which powers life on Earth, is a mere speck in the grand cosmic tapestry when compared to a star like UY Scuti. Yet, despite its immense size, even UY Scuti is fleeting in the grand timeline of the universe. As a red supergiant, UY Scuti exists in a phase that will last only a few million years, a short life compared to stars like our Sun, which can shine for billions of years. This underscores the fact that in the universe, nothing is truly permanent. Everything is in a constant state of flux. The idea of time itself, when applied to these massive cosmic entities, becomes something truly mind-bending. One of the most fascinating aspects of UY Scuti is its role in the ongoing cosmic evolution. As a massive star, it plays a key part in the enrichment of the universe's chemical composition. The elements that make up our bodies and the planets we live on were forged in the hearts of stars like UY Scuti. As UY Scuti reaches the end of its life, it will likely go supernova, expelling enormous amounts of energy and material into space. This explosion will not only mark the end of the star but will also distribute heavy elements like iron, nickel, and gold into the interstellar medium, enriching the gas clouds from which future stars and planets will form. In essence, UY Scuti is helping to create the building blocks for the next generation of stars and planetary systems, continuing the cosmic cycle of life and death. The energy released during such an event is beyond anything we can imagine. A supernova explosion can release more energy in a single second than our Sun will emit throughout its entire lifespan. This explosion is so powerful that it can briefly outshine an entire galaxy. The shockwaves generated by the supernova can compress nearby gas clouds, sparking the birth of new stars. As these stars form, they can carry with them the elements created in the supernova, setting the stage for the creation of planets and, potentially, life. But even before its eventual demise, UY Scuti plays a vital role in the cosmic ecosystem. The immense energy radiated by the star influences its surroundings in ways that are only beginning to be understood. The stellar wind, streams of charged particles blowing away from the star at incredible speeds, shapes the interstellar medium, pushing gas and dust outwards and affecting the formation of nearby stars. This interaction between UY Scuti and its environment creates a ripple effect across the galaxy, influencing the dynamics of the entire region around it. We must also consider the effect of such massive stars on the structure of galaxies. Massive stars like UY Scuti can affect the gravitational dynamics of their host galaxies, particularly when they are part of a star cluster or a binary system. The gravitational pull of these stars can distort the orbits of other stars and planetary systems, causing shifts in the overall structure of the galaxy. The death of such a star, especially if it results in a supernova or the formation of a black hole, can trigger even more dramatic changes, potentially leading to the formation of new stellar clusters or altering the course of galactic evolution. In addition to its role in the formation of elements and the redistribution of material across the universe, UY Scuti's sheer size offers insights into the mechanisms that govern stellar structure and evolution. The fact that UY Scuti is one of the largest stars ever discovered by radius suggests that there are aspects of stellar life cycles we are only beginning to understand. How do stars like UY Scuti manage to expand to such vast sizes? What is the internal structure of these stars? What forces keep them from collapsing under their immense gravitational pull? These questions are central to the study of stellar physics. Stars like UY Scuti do not behave like smaller stars. Their immense size means that they are subject to different physical processes and forces. The balance between radiation pressure, the outward force from the energy generated by nuclear fusion, and the inward pull of gravity is delicate in a star like UY Scuti. As the star expands, it becomes increasingly unstable. Small changes in its internal processes can have dramatic effects on the star's structure. For example, fluctuations in the core's fusion processes can lead to the outer layers expanding and contracting, creating what are known as stellar pulsations. These pulsations cause the star to periodically change size, becoming brighter or dimmer as its outer layers expand and contract. Another fascinating aspect of UY Scuti's life is its potential for variability. Red supergiants like UY Scuti are known to be variable stars, meaning their brightness changes over time. These variations can occur on timescales ranging from hours to years, and the cause of these variations is still an area of active research. The pulsations that occur within the star's interior can cause the outer layers to move, creating fluctuations in brightness. These variations are not simply random, they are the result of complex interactions between the star's core and its outer layers. The study of UY Scuti and other red supergiants also sheds light on the evolution of the universe itself. These stars are often considered end-of-life stars because their large size and intense luminosity mean that they burn through their nuclear fuel quickly. This rapid consumption of fuel accelerates their evolution, leading them to exhaust their energy reserves long before smaller stars like our Sun. However, the death of UY Scuti will not be the end of its influence. Instead, it will mark the beginning of a new chapter in the cosmic cycle, one that will continue to shape the future of the universe. There's also a profound philosophical aspect to the study of stars like UY Scuti. The sheer scale of such a star, and the recognition that it is only one of billions in our galaxy, forces us to confront our place in the cosmos. It's humbling to think that we live on a small, rocky planet orbiting a medium-sized star, in a galaxy that is just one among countless others scattered throughout the universe. And yet, despite the vastness of the universe, the study of stars like UY Scuti brings us closer to understanding the fundamental processes that govern all of existence. As we continue to study stars like UY Scuti, we also learn more about the potential for life elsewhere in the universe. The elements produced in stars like UY Scuti are essential for the formation of planets, and the explosion of such stars through supernovae enriches the interstellar medium with these elements. Could these elements eventually lead to the formation of planets that could harbor life? Could some of the building blocks for life exist on planets orbiting stars in other galaxies? The possibilities are vast, and the study of UY Scuti and similar stars helps to expand our understanding of where and how life might arise beyond our planet. UY Scuti is not just a large, distant star. It is a key piece in the larger puzzle of the universe. Through its massive size, its life cycle, and its eventual death, UY Scuti contributes to the ongoing process of cosmic evolution. The study of such stars not only helps us understand the physics of stellar life and death but also provides a glimpse into the history of the universe and the future of galaxies, stars, and planets. It serves as a reminder that the universe is far more complex and dynamic than we can fully comprehend, and that each discovery about stars like UY Scuti brings us one step closer to understanding the vast and interconnected web of cosmic processes that shape the universe we live in. As we delve deeper into the study of UY Scuti, it's essential to acknowledge that these stars, while extraordinary, are not isolated entities. They belong to a vast ecosystem of stars, galaxies, and cosmic phenomena that influence one another. UY Scuti is but a single example of the remarkable diversity of stellar types across the universe, each contributing to the grand, intricate process that drives the evolution of the cosmos. UY Scuti's significance is underscored by its position within the class of red supergiants, a group of stars that are known for their massive size and relatively short lifespans. These stars are in a later stage of stellar evolution, having exhausted the hydrogen fuel in their cores and transitioned to the fusion of heavier elements like helium, carbon, and oxygen. This phase is known as the red giant, or red supergiant phase. These stars are characterized by their vast, inflated outer layers, which extend well beyond the size of our Sun. In the case of UY Scuti, the physical size is almost incomprehensible. With a radius around 1,700 times that of the Sun, UY Scuti dwarfs our solar system. If it were placed at the center of our solar system, its outer layers would extend beyond the orbit of Jupiter, consuming Mercury, Venus, Earth, Mars, and perhaps even Jupiter itself. This gives us a sense of just how large UY Scuti is, and how this scale creates an awe-inspiring perspective on the nature of stars. Its vast size, however, does not translate into an equivalent mass. UY Scuti's mass is only about 30 times that of the Sun. This discrepancy between size and mass is a hallmark of red supergiants, which are less dense than smaller stars, but much more voluminous. The low density of UY Scuti compared to its size has important implications for its internal structure and behavior. Unlike smaller, more compact stars, red supergiants like UY Scuti experience extensive internal convective motions. These motions occur in the star's outer layers and are responsible for transporting energy from the core to the surface. In the case of UY Scuti, these convection currents are so intense that they can cause dramatic changes in the star's outer appearance. The star's surface may appear to be pulsating, expanding and contracting over time as it undergoes thermal oscillations. This variability is a characteristic feature of stars like UY Scuti, and these oscillations are often studied by astronomers to better understand the complex processes that govern stellar evolution. These pulsations in stars like UY Scuti are known as radial pulsations, and they occur when a star's outer layers move outward and inward due to changes in the internal pressure and temperature. As the outer layers expand, the star's luminosity increases, and as they contract, the luminosity decreases. This pulsating behavior leads to fluctuations in brightness, and these variations can sometimes be detected as periodic changes in the star's light output. This variability provides astronomers with crucial data that can be used to model the internal dynamics of the star. By studying the way a star like UY Scuti changes over time, astronomers can learn about its internal composition, temperature distribution, and the forces at work within its core. While the study of stellar pulsations is fascinating in its own right, it is also crucial for understanding the broader mechanics of stellar evolution. The behavior of red supergiants like UY Scuti reveals important details about the life cycle of massive stars. When a star like UY Scuti enters the red supergiant phase, it is nearing the end of its life. The fuel in its core has been exhausted, and the star is no longer able to maintain the delicate balance between gravity and pressure that keeps it stable. As a result, the core contracts under the force of gravity, while the outer layers expand outward. This expansion causes the star to become increasingly luminous and cooler, giving it the characteristic red color of a red giant or supergiant. But UY Scuti's eventual fate is not a quiet one. As a red supergiant, it is fated to undergo a dramatic transformation. Once the core has contracted to a critical point, the pressure and temperature will become so extreme that nuclear fusion will begin in the core once again, this time producing heavier elements such as carbon and oxygen. The star will continue to burn through its fuel, causing it to expand and contract over time. Eventually, the core will collapse, and the outer layers will be ejected into space in a violent supernova explosion. This is the final stage in the life cycle of a red supergiant, and it marks the end of the star's life. The supernova that results from UY Scuti's death will be an extraordinary event, releasing an enormous amount of energy and light. Supernovae are among the most powerful explosions in the universe, and they can briefly outshine entire galaxies. The explosion will scatter the star's outer layers across space, enriching the interstellar medium with heavy elements like iron, nickel, and gold. These elements, formed in the cores of stars like UY Scuti, are crucial for the formation of new stars, planets, and even life itself. The shockwaves from the supernova will also trigger the formation of new stars, and in this way, UY Scuti's death will give rise to the next generation of stellar systems. It is worth noting that not all red supergiants meet the same end. Some, like UY Scuti, will end their lives in a spectacular supernova explosion, while others may undergo a different fate. If a star is massive enough, the collapse of its core can lead to the formation of a black hole. The exact conditions that determine whether a star will form a black hole or a neutron star after a supernova are still the subject of intense research, but the process is one of the most mysterious and fascinating aspects of stellar evolution. The formation of black holes from the death of massive stars like UY Scuti is a key area of study in modern astrophysics. A black hole forms when the core of a star collapses to a point of infinite density, creating a region of space where the gravitational pull is so strong that nothing, not even light, can escape. These enigmatic objects are the subject of intense fascination and have been at the forefront of scientific inquiry in recent years. The study of black holes helps to deepen our understanding of general relativity, quantum mechanics, and the very nature of space and time. Despite its eventual collapse, UY Scuti's death will not mark the end of its influence on the universe. The elements released during the supernova will continue to play a role in the formation of new stars and planetary systems. These elements, forged in the cores of massive stars like UY Scuti, are the building blocks of the universe. The iron in our blood, the calcium in our bones, and the carbon in our cells were all created in the cores of stars long before our solar system even existed. In a sense, we are all made of stardust, and UY Scuti's death will help to continue this process, ensuring that the cycle of stellar birth, death, and rebirth continues. In the grand scheme of things, UY Scuti is just one of billions of stars in our Milky Way galaxy, and it is dwarfed by even larger stars that exist beyond our observation. Yet, its size, its fate, and its role in the cosmic cycle make it an important object of study. As we learn more about UY Scuti and stars like it, we also learn more about the nature of the universe itself, and about the forces that drive the birth, evolution, and death of stars. Each new discovery about stars like UY Scuti brings us closer to understanding the fundamental processes that shape the cosmos, and our place within it. UY Scuti's fascinating life cycle, from its birth in a star-forming nebula to its eventual death in a spectacular supernova explosion, tells us much about the nature of stars, the universe, and even the very elements that make up our own bodies. As we continue exploring the mysteries surrounding UY Scuti, it is essential to keep in mind that its immense size is not just a physical measurement, but a window into the vastness of the universe itself. Stars like UY Scuti exist in a delicate balance of forces and pressures, and their existence provides valuable insights into the processes that govern the cosmos. One of the most profound aspects of studying UY Scuti is the sheer scale at which it operates. The star's immense radius, around 1,700 times that of the Sun, and its correspondingly vast luminosity, place it in the realm of the most extreme stellar objects in the universe. Its size challenges our understanding of space and the forces that shape it. However, this scale is not just about numbers, it's about the context in which these stars exist. UY Scuti's size, and the way it fits into the broader ecosystem of stars, galaxies, and cosmic phenomena, gives us a deeper appreciation for the complexity of the universe. As we look beyond UY Scuti, we find that its story is not unique. In fact, UY Scuti is part of a broader category of stars known as red supergiants, a group that includes some of the largest, most luminous stars ever discovered. These stars, while not as common as smaller, more stable stars like our Sun, play a crucial role in the evolution of galaxies. Red supergiants are massive, often reaching masses between 10 to 30 times that of the Sun, and they burn through their nuclear fuel at an extraordinarily fast rate. The energy produced by these stars is so immense that it often outshines entire galaxies, making red supergiants among the most visible and dynamic objects in the universe. However, red supergiants are short-lived in cosmic terms. Their rapid consumption of fuel means they burn out quickly, leaving behind a legacy of heavy elements that enrich the surrounding space. This process of stellar death and rebirth is an ongoing cycle in the universe, one that is crucial to the formation of new stars, planets, and even life itself. By studying red supergiants like UY Scuti, scientists gain a better understanding of the mechanisms behind this process and the role that massive stars play in shaping the cosmos. It is important to note that UY Scuti's size is not a permanent characteristic. The star is not in a stable, static phase but is instead constantly evolving, undergoing changes that will eventually lead to its demise. The fact that UY Scuti is so massive and so luminous means that it burns through its fuel at an accelerated rate. As the star exhausts its hydrogen supply, it will move on to fuse heavier elements like helium, carbon, and oxygen, undergoing changes in size, temperature, and luminosity as it goes through the various stages of stellar evolution. Over time, it will expand into a red supergiant and eventually experience a cataclysmic supernova explosion. This transformation is not unique to UY Scuti. It is a universal process that all massive stars undergo. As a star progresses through its life cycle, it undergoes changes in its core, which lead to changes in its outer layers. These changes are driven by complex nuclear processes, with elements undergoing fusion at the core, creating heavier and heavier elements as the star ages. This progression is inevitable for any massive star, and it is this cycle of birth, life, and death that drives the ongoing evolution of galaxies and star systems across the universe. In addition to its sheer size and luminosity, UY Scuti's behavior as a variable star adds another layer of intrigue. As a pulsating red supergiant, UY Scuti is not a steady, unchanging object. Instead, its brightness fluctuates over time due to its pulsations, a phenomenon that occurs when a star's outer layers expand and contract. These variations in brightness, while not necessarily noticeable to the naked eye, are critical to astronomers, as they provide valuable insights into the internal dynamics of the star. By studying the light curves of stars like UY Scuti, astronomers can learn about the star's internal composition, temperature, and pressure, providing a clearer picture of how these massive objects evolve over time. UY Scuti's variability, while fascinating, also poses significant challenges for astronomers. The star's pulsations make it difficult to pinpoint its exact size, distance, and other characteristics. The variability in brightness means that the star's light output is constantly changing, making it challenging to obtain consistent measurements over time. However, advances in technology, such as space telescopes and high-resolution spectrographs, have allowed astronomers to measure the light from UY Scuti with greater precision. These measurements provide a more accurate picture of the star's properties and help to refine our understanding of the processes that govern the behavior of red supergiants. As we look to the future, it is clear that UY Scuti and stars like it will continue to play a crucial role in our understanding of the universe. By studying these massive objects, we gain insight not only into the life cycles of individual stars but also into the broader dynamics of galaxies, star formation, and the distribution of elements throughout the cosmos. The death of a star like UY Scuti will have far-reaching consequences, enriching the interstellar medium with heavy elements and contributing to the formation of new stars and planets. In this way, the cycle of stellar birth and death is inextricably linked to the ongoing evolution of the universe itself. In the broader context of the cosmos, UY Scuti's size and properties help to illustrate the vast scale of the universe. While our own Sun is an average-sized star, it is hard to imagine just how small it is compared to some of the most massive stars in the galaxy. UY Scuti, along with other red supergiants and hypergiants, serves as a reminder of the incredible diversity of stars that populate the universe. These stars, though fleeting in their lifetimes, leave behind a lasting legacy in the form of the elements they create and the gravitational forces they exert on their surroundings. Moreover, the study of stars like UY Scuti challenges our understanding of physics. These massive stars operate under conditions that are difficult to replicate on Earth. The extreme pressures, temperatures, and magnetic fields within stars like UY Scuti push the boundaries of our understanding of fundamental forces like gravity and nuclear fusion. By studying these objects, scientists are able to test theories of stellar physics, nuclear fusion, and even the behavior of matter under extreme conditions. These insights not only improve our understanding of stellar evolution but also help to refine our knowledge of the fundamental laws of the universe. As we continue to explore the far reaches of the universe, the study of stars like UY Scuti remains one of the most exciting and rewarding areas of scientific inquiry. With advancements in technology and new observational techniques, we are likely to uncover even more about the enigmatic behavior of these massive stars. Whether it's studying their pulsations, measuring their size and luminosity, or investigating the mechanics of their death, the exploration of UY Scuti and its counterparts will continue to deepen our understanding of the cosmos. The lessons we learn from UY Scuti are not just about the star itself but also about the nature of the universe as a whole. By studying these colossal stars, we gain a better appreciation for the scale of the cosmos and the processes that drive its evolution. We learn about the interconnectedness of stars, galaxies, and the interstellar medium, and we come to understand that the life and death of a star is not an isolated event but part of an ongoing cycle that shapes the universe. In many ways, the story of UY Scuti is a reflection of the broader narrative of the universe itself, a story of birth, transformation, and rebirth that spans billions of years and will continue long after the death of this particular star. As we continue our journey through the remarkable tale of UY Scuti, we realize that its size and behavior offer us profound insights into the nature of the universe. The star serves as both a scientific puzzle and a reminder of how much we still have to learn about the cosmos. Stars like UY Scuti are not just the largest known objects by radius, but they also provide critical clues to the life cycle of stars and the processes that occur within them. The fascinating evolution of a star like UY Scuti begins with its birth in the heart of a molecular cloud, a vast, cold, and dense region of gas and dust. In these clouds, gravity begins to take hold, causing material to collapse inward. As the gas and dust compress, they heat up, eventually reaching temperatures and pressures sufficient for nuclear fusion to begin. It is this fusion process that powers stars, including UY Scuti, and it is through this process that stars generate the energy required to shine for billions of years. For UY Scuti, as for all stars, its life is characterized by a delicate balance between the outward pressure of radiation from fusion and the inward pull of gravity. In the case of red supergiants like UY Scuti, this balance becomes more tenuous as the star reaches the end of its life. The star's core begins to burn through the hydrogen in its fuel reserves at an accelerating rate, eventually exhausting the supply. At this point, the core contracts and heats up, while the outer layers of the star expand dramatically, transforming it into a supergiant. As the star continues to expand, its outer layers cool, giving the star its distinctive reddish hue. This cooling is a result of the decreased rate of nuclear fusion in the outer layers of the star, as the core reaches temperatures that are high enough to fuse heavier elements like helium and carbon. These elements, in turn, undergo their own fusion processes, creating even heavier elements such as oxygen, neon, and silicon. The fusion of these heavier elements in the core leads to the formation of a series of concentric shells, each composed of a different element in varying stages of fusion. UY Scuti, being one of the largest stars in the known universe, has a core that is rich in these heavy elements, while its outer layers are primarily composed of hydrogen and helium. The presence of these elements within the star's interior plays a crucial role in its eventual fate. As UY Scuti burns through its fuel, it will eventually reach a point where the fusion process becomes unsustainable. The core will no longer be able to generate enough energy to counteract the pull of gravity, and the star will undergo a catastrophic collapse. The fate of UY Scuti is tied to the concept of a supernova, an incredibly powerful explosion that occurs when a massive star runs out of fuel and can no longer sustain itself. When the core of UY Scuti collapses, it will release an enormous amount of energy in the form of radiation and shock waves, causing the outer layers of the star to be ejected into space. These ejected materials will enrich the surrounding interstellar medium with heavy elements, including those formed in the star's core, such as oxygen, carbon, and iron. This explosion will mark the end of UY Scuti's life, but it will also provide the raw materials for the formation of new stars, planets, and even life itself. The elements produced in the explosion will mix with other interstellar material, leading to the creation of new stellar systems. In this sense, the death of a star like UY Scuti is not an end, but a beginning, a new cycle of stellar evolution that will shape the future of the cosmos. The energy released during the supernova of a red supergiant like UY Scuti is so immense that it can briefly outshine an entire galaxy. This spectacular event is visible across vast distances, and astronomers often detect the light from these explosions long after the star has perished. The study of supernovae, particularly those from massive stars like UY Scuti, provides valuable insights into the processes that govern the death of stars and the distribution of elements throughout the universe. The remnants of such supernovae can be observed as nebulae and pulsars, which continue to provide valuable data for scientists studying the life cycles of stars. While UY Scuti's eventual supernova is inevitable, it will not occur for many millions of years. In the meantime, the star will continue its pulsations, expanding and contracting as it oscillates through its life cycle. These pulsations, as previously mentioned, provide astronomers with key information about the internal structure of the star. By studying these variations in brightness, scientists can learn more about the processes occurring deep within the star's core. The study of pulsating stars is a field of research known as astroseismology, and it has provided some of the most detailed insights into the interior workings of stars like UY Scuti. Astroseismology works by measuring the frequencies of oscillations in a star's light. These oscillations are similar to seismic waves on Earth, and by analyzing them, scientists can infer properties about the star's internal structure, such as its temperature, density, and chemical composition. This method has proven to be incredibly effective, and it has allowed astronomers to refine their models of stellar interiors. By applying astroseismology to UY Scuti, researchers can gain a better understanding of the physical conditions within this massive star, shedding light on the processes that lead to its eventual collapse. In addition to its pulsations, UY Scuti's vast size means that it is also one of the most luminous stars known. Its luminosity, which is roughly 350,000 times that of the Sun, is a direct consequence of its massive size and the tremendous amount of energy it generates through nuclear fusion. The energy produced by the fusion of hydrogen in the core of the star is radiated outward, heating the star's outer layers to temperatures of several thousand degrees. This energy not only causes the star to shine brightly but also exerts an outward pressure that keeps the star from collapsing under its own gravity. However, as UY Scuti ages, it will begin to lose mass through powerful stellar winds. These winds, which are streams of charged particles ejected from the outer layers of the star, gradually strip away the star's mass over time. The mass loss of a star like UY Scuti is a key factor in its evolution, as it influences the star's temperature, luminosity, and size. As the star loses mass, its outer layers will become less stable, and the rate of fusion in the core will slow down. This will cause the star to cool and expand, eventually transforming it into a red supergiant. The process of mass loss through stellar winds is a critical aspect of the life cycle of massive stars. These winds are responsible for shaping the star's outer layers and playing a crucial role in the creation of elements that are essential for the formation of planets and life. The material ejected by the star during its lifetime will eventually mix with the interstellar medium, contributing to the formation of new stars, planets, and even the building blocks of life. The mass loss of UY Scuti will continue until the star reaches the end of its life. Once it exhausts its nuclear fuel, the core will collapse, and the outer layers will be ejected in a spectacular supernova explosion. The elements produced in this explosion will enrich the surrounding space, contributing to the formation of new stars and planetary systems. In the final stages of its life, UY Scuti will transform into a supernova remnant, a cloud of gas and dust that contains the elements created during the star's lifetime. The explosion of the supernova will trigger the formation of new stars and planets, and the cycle of stellar birth and death will continue. For astronomers, the study of supernova remnants provides valuable information about the processes that govern the death of massive stars and the distribution of elements throughout the galaxy. UY Scuti, like all stars, will have a profound impact on the universe. Its size, luminosity, and eventual demise will help shape the interstellar medium and contribute to the creation of new stars and planets. Through the study of UY Scuti, we gain a deeper understanding of the universe and the processes that govern the formation and evolution of stars. The story of UY Scuti is not just the story of one massive star, but the story of the universe itself, a dynamic, ever-changing process of creation, transformation, and rebirth. As we continue our exploration of UY Scuti, we find ourselves at the threshold of deeper questions about the nature of massive stars and the role they play in the larger cosmic framework. The life cycle of a star like UY Scuti offers us an intricate view into the fundamental processes that govern the evolution of celestial bodies. From its birth to its eventual collapse, UY Scuti serves as a striking example of the dramatic and awe-inspiring events that unfold in the universe on a grand scale. Stars like UY Scuti are often classified as variable stars, which means that their brightness fluctuates over time. This variability is a key characteristic of many red supergiants, including UY Scuti. These fluctuations are caused by changes in the star's outer layers, where complex interactions between the star's internal processes and external factors such as stellar winds and temperature gradients lead to periodic changes in luminosity. The pulsations of UY Scuti are some of the most fascinating aspects of its behavior and are central to understanding the star's dynamic nature. UY Scuti's variability is tied to its position on the Hertzsprung-Russell diagram, a graphical representation of stars based on their luminosity and temperature. Red supergiants like UY Scuti occupy the upper right portion of the diagram, where they are characterized by their immense size and low surface temperatures. These stars are typically in the later stages of their evolution, having exhausted their hydrogen fuel and begun the process of burning heavier elements. As they do so, their outer envelopes expand and contract, leading to the observed variations in brightness. Interestingly, the pulsations of stars like UY Scuti are not random. Instead, they follow a predictable pattern, with the star's outer layers oscillating in a manner that allows astronomers to study the physical properties of the star. The period of these pulsations can range from a few days to several months, depending on the size and mass of the star. By carefully observing the patterns of these pulsations, astronomers can gain valuable insights into the structure and composition of the star, including its internal temperature, density, and pressure. The study of UY Scuti's pulsations also opens up a broader discussion about the impact of stellar variability on the surrounding interstellar medium. As UY Scuti expands and contracts, it generates significant turbulence in the space surrounding it. This turbulence can affect the movement of gas and dust in the vicinity of the star, creating conditions that may promote the formation of new stars and planetary systems. In a sense, the pulsations of UY Scuti act as a cosmic engine that drives the movement of matter throughout its local environment, contributing to the ongoing cycle of star birth, life, and death. One of the most intriguing aspects of UY Scuti is its size. While its mass is not as extreme as some of the most massive stars, its radius is truly mind-boggling. If placed at the center of our solar system, UY Scuti would extend far beyond the orbit of Jupiter, engulfing the orbits of Mercury, Venus, Earth, and Mars. This gives us a tangible sense of the scale of the star and emphasizes just how different it is from our own Sun, which is relatively modest in comparison. UY Scuti's sheer size is a testament to the incredible forces at work in the universe, and it challenges our understanding of what is possible in terms of stellar dimensions. The size of a star like UY Scuti is determined by several factors, including its mass, age, and the nature of its fusion processes. In the case of red supergiants, the star's size is a reflection of the complex interplay between the gravitational forces acting to collapse the star and the outward pressure created by the fusion of heavy elements in its core. The larger the star, the greater the outward pressure required to counteract the gravitational pull, which leads to a larger and more diffuse outer envelope. While UY Scuti's size is awe-inspiring, it is important to note that its massive dimensions come with significant consequences for the star's stability. The larger a star becomes, the less stable it becomes, as the outward pressure generated by nuclear fusion becomes increasingly difficult to maintain. For a star like UY Scuti, this instability is manifested in the pulsations and variability that characterize its behavior. As the star's core exhausts its fuel, its outer layers will continue to expand and contract, causing the star to become even more unstable. Eventually, this instability will lead to the star's eventual collapse, culminating in a dramatic supernova explosion. The fate of UY Scuti as it reaches the end of its life will likely be a spectacular one. Once it exhausts its nuclear fuel, the star will no longer be able to sustain the fusion reactions necessary to keep its core from collapsing under the force of gravity. As the core contracts and heats up, it will eventually reach temperatures sufficient to fuse heavier elements like carbon, neon, and oxygen. These elements will undergo fusion in the core, releasing enormous amounts of energy, and causing the outer layers of the star to expand even further. As the star's outer envelope continues to expand, it will eventually shed a significant portion of its mass, losing material through powerful stellar winds. These stellar winds will carry away much of the star's outer layers, leaving behind a dense and hot core. This core, composed mostly of iron and other heavy elements, will continue to contract until it reaches a point where no known forces can prevent it from collapsing further. At this point, the core will undergo a catastrophic collapse, triggering a supernova explosion that will release an enormous amount of energy and light. This explosion will briefly outshine an entire galaxy, and the shockwave from the explosion will trigger the formation of new stars and planetary systems in the surrounding space. The death of a star like UY Scuti is not just the end of a single star. It is a cosmic event that has far-reaching consequences for the galaxy and the universe as a whole. The elements produced in the star's core during its lifetime, including those created in the final stages of its collapse, will be dispersed into space during the supernova explosion. These elements will mix with other interstellar material, contributing to the formation of new stars, planets, and even the building blocks of life. In this way, the death of a star like UY Scuti is not an end but a beginning, a new chapter in the ongoing cycle of cosmic creation. The explosion of UY Scuti will also have a profound impact on the surrounding environment. The shockwaves from the supernova will compress the interstellar gas and dust in the vicinity of the star, triggering the formation of new stars and planets. This process, known as star formation, is a fundamental aspect of the evolution of galaxies, and it is one of the ways in which the universe replenishes itself with new stars. The elements produced in the explosion will also play a crucial role in the formation of planets and other celestial bodies, enriching the material from which new planetary systems are made. The study of UY Scuti's eventual demise is a key area of research in the field of astrophysics, as it offers valuable insights into the life cycle of massive stars and the processes that govern the evolution of galaxies. By studying the behavior of stars like UY Scuti, scientists can refine their models of stellar evolution and improve their understanding of the broader processes that shape the universe. Moreover, the study of supernovae and their remnants provides valuable clues about the distribution of heavy elements throughout the galaxy, helping astronomers trace the history of star formation and the chemical evolution of the universe. UY Scuti, with its immense size and complexity, serves as a remarkable laboratory for understanding the life cycles of stars and the processes that govern the universe. Its pulsations, variability, and eventual collapse offer a wealth of information for scientists seeking to unravel the mysteries of the cosmos. The star is a cosmic giant, but it is also a symbol of the vast and intricate processes that shape the universe, from the birth of stars to their death and rebirth in the form of new generations of celestial bodies. As we peer into the future of UY Scuti, we are reminded of the fleeting nature of all things in the cosmos. Stars like UY Scuti may burn brightly for millions or even billions of years, but they are ultimately subject to the same fate as all stars, a dramatic and inevitable death that marks the end of their stellar journey. Yet, as one star dies, another is born, and the cycle of creation continues. The story of UY Scuti is not just the story of one star, but the story of the universe itself, a dynamic and ever-changing process of birth, death, and rebirth. As we continue to explore UY Scuti, we find ourselves on the brink of discovering more about the cosmic mechanics behind its massive size and the interplay of forces that govern stars of its type. It's easy to be captivated by UY Scuti's immense radius, but this star, like all other celestial bodies, exists as part of a much larger and more complex system of forces, interactions, and phenomena that shape the very fabric of the universe. UY Scuti's sheer size and variability are not merely the result of random cosmic forces. They are the consequences of the intricate dance between the star's mass, age, and chemical composition. These stars, including UY Scuti, are the product of billions of years of cosmic evolution, beginning with the primordial hydrogen and helium that formed after the Big Bang. The stars we see today are the culmination of countless generations of star formation, death, and rebirth, each leaving behind essential elements that will eventually form new stars and planets. One of the more remarkable features of stars like UY Scuti is their internal structure. The core of the star, where nuclear fusion occurs, is a place of extreme temperatures and pressures. The temperature of UY Scuti's core is believed to reach tens of millions of degrees Celsius, enough to fuse the heaviest elements, such as carbon and oxygen, in the nuclear reactions that power the star. However, while the core is intensely hot and dense, the outer layers of UY Scuti are much cooler and more diffuse, allowing us to observe its reddish glow. This stark contrast between the inner and outer layers of the star is a characteristic feature of red supergiants. The outer layers of the star are constantly in flux, expanding and contracting in response to the internal pressure from nuclear fusion. These pulsations are what cause UY Scuti's variability in brightness. As the star's outer layers move, the amount of light emitted by the star changes, leading to the observed fluctuations in luminosity. This behavior is similar to that of other pulsating stars, such as Cepheid variables, and provides key insights into the physics of these massive celestial bodies. The star's mass plays a crucial role in determining its evolution. While UY Scuti's mass is not the largest among stars, it is still massive enough to undergo a relatively short life cycle compared to smaller stars like our Sun. Over the course of millions of years, the star will exhaust its fuel, and the core will eventually collapse under the immense pressure of gravity. This collapse will trigger a supernova explosion, which will mark the end of UY Scuti's life as a star. The explosion will release vast amounts of energy and eject the outer layers of the star into space, enriching the interstellar medium with heavy elements like iron, nickel, and other metals. These elements are critical for the formation of new stars, planets, and even life itself. While the physical processes within UY Scuti are fascinating, the star also provides a unique perspective on the evolution of galaxies. UY Scuti is part of a complex cosmic ecosystem, influenced by and contributing to the greater galactic environment. Its massive size and eventual death will have far-reaching effects on the surrounding space, impacting the dynamics of the galaxy as a whole. The elements produced during its lifetime, particularly during its final stages, will be spread throughout the galaxy, contributing to the chemical enrichment of the interstellar medium. This enrichment is essential for the formation of new stars and planetary systems, as it provides the building blocks for the next generation of celestial bodies. The story of UY Scuti is not just one of individual stars but also a story of the ongoing processes that shape galaxies. Stars like UY Scuti are the cosmic engines that drive the formation of new material and the evolution of the universe itself. They provide the raw materials for the creation of new stars, planets, and life, ensuring the continuous cycle of cosmic rebirth. Their death, often in the form of a supernova explosion, acts as a catalyst for the formation of new structures in the galaxy, making their eventual demise an essential part of the cosmic cycle. As we look toward the future of UY Scuti, we can't help but imagine how the remnants of this massive star will contribute to the broader cosmic landscape. After the star's explosion, the remaining core may collapse into a neutron star or black hole, depending on its mass and the details of its collapse. The surrounding nebula, formed from the expelled material, will gradually disperse into space, eventually mixing with other interstellar gas and dust. This material may later condense to form new stars or even planets, continuing the cycle of cosmic creation. The exact details of how UY Scuti's death will unfold remain uncertain, as we still have much to learn about the evolution of red supergiants and their supernova explosions. However, the general principles are well understood. The energy released during the final stages of a star's life can trigger a series of processes that shape the future of the surrounding space. These processes include the formation of new stars and the distribution of heavy elements that are essential for the creation of planets and life. Stars like UY Scuti are also crucial to our understanding of stellar nucleosynthesis, the process by which elements are formed in the cores of stars. As these massive stars burn through their nuclear fuel, they create heavier elements through a series of fusion reactions. These elements are then released into space during the star's death, enriching the interstellar medium and contributing to the formation of new stars and planetary systems. The heavy elements formed in stars like UY Scuti are responsible for creating the elements that make up planets, including Earth. This connection between the death of stars and the formation of new worlds is one of the most profound aspects of astrophysics. UY Scuti, in many ways, serves as a reminder of the scale and power of the universe. Its enormous size, dynamic behavior, and eventual fate are all part of the intricate web of cosmic events that shape the galaxy and beyond. As we continue to observe and study stars like UY Scuti, we gain valuable insights into the fundamental processes that govern the evolution of the universe. Each discovery brings us closer to understanding not just the life of this particular star but the broader mechanisms that drive the creation and destruction of celestial bodies across the cosmos. UY Scuti stands as one of the most remarkable objects in our galaxy, not just because of its immense size but also because it offers a window into the incredible processes that shape the cosmos. Its pulsations, variability, and eventual demise will continue to captivate astronomers for generations to come, providing insights into the nature of massive stars and the ongoing evolution of galaxies. The story of UY Scuti is the story of stars themselves, brief, brilliant, and ultimately subject to the same cosmic laws that govern all celestial bodies. It serves as a testament to the dynamic and ever-changing nature of the universe, where every star, no matter how large, will one day meet its end, only to give birth to something new. The story of UY Scuti, as we have delved into so far, is a narrative that transcends the life of one star and reflects the broader processes that define the universe itself. It's a story of birth, transformation, death, and rebirth, showing how each cosmic event feeds into the next. We've touched on the stages of a star's life, its core processes, its influence on the interstellar medium, and its eventual demise. Yet, what makes UY Scuti especially intriguing is how it provides a glimpse into the nature of extreme astrophysical phenomena that we still seek to understand more fully. As a red supergiant, UY Scuti is in the final phase of its life cycle, but this doesn't mean its legacy is over. In fact, its eventual supernova will give rise to a series of events that affect not only the immediate vicinity, but also the galaxy at large. In the aftermath of the explosion, the core remnant may collapse into a black hole or neutron star, phenomena that themselves are subjects of intense interest within the field of astrophysics. The dynamics of supernova explosions are not fully understood, particularly the exact mechanisms behind the formation of neutron stars and black holes. Supernovae are one of the most energetic events in the universe, releasing an enormous amount of energy and creating shock waves that propagate through space. These shock waves are responsible for triggering the formation of new stars and planetary systems. When UY Scuti eventually dies, its supernova explosion will send a shockwave through the surrounding nebula, scattering heavy elements throughout space. These elements will become part of the material that eventually forms new stars, planets, and even the building blocks of life. The black hole or neutron star that may form from UY Scuti's collapse is a fascinating possibility. Black holes, objects of immense gravity that not even light can escape, remain one of the most mysterious phenomena in astrophysics. A neutron star, on the other hand, is a dense, compact remnant of a massive star, composed mostly of neutrons. Both of these objects are exotic in their properties and behave in ways that defy our everyday understanding of physics. The formation of black holes and neutron stars involves extreme conditions of density and pressure, far beyond anything we experience on Earth. Neutron stars are typically only about 20 kilometers in diameter but contain a mass greater than that of the Sun. These stars are the remnants of stars that were massive enough to collapse into this ultra-dense state. In a neutron star, the force of gravity is so strong that it compresses the atoms to the point where only neutrons remain, resulting in an incredibly compact object. Black holes, on the other hand, are even more perplexing. These objects are so dense that they warp spacetime itself, creating a singularity, a point of infinite density. At the center of a black hole, time and space behave in ways that defy the laws of physics as we understand them. The study of black holes has become a cornerstone of modern astrophysics, as they challenge our concepts of gravity, space, and time. The study of stars like UY Scuti, which may eventually collapse into such objects, helps us to explore these fundamental questions. But the effects of UY Scuti's eventual demise extend beyond the creation of exotic objects like black holes and neutron stars. The explosion of such a massive star enriches the interstellar medium with heavy elements, including iron, carbon, oxygen, and more. These elements are critical to the formation of planets and life as we know it. In fact, many of the elements that make up the Earth and other planets in our solar system were created in the cores of stars that lived and died long before our Sun was born. When UY Scuti dies, it will contribute to this ongoing cycle of stellar birth and death that has shaped the universe for billions of years. What makes this particularly fascinating is the realization that all life on Earth is made from the very materials that stars like UY Scuti create. The carbon in our bodies, the oxygen we breathe, the iron in our blood, all of these elements were forged in the cores of stars. UY Scuti, despite being an incredibly distant and seemingly detached object, plays a crucial role in the ongoing process of creating the building blocks of life. This is the interconnectedness of the universe in action, a cosmic cycle of creation, destruction, and regeneration that spans billions of years and takes place on a scale far beyond human comprehension. As we turn our attention to the future, we can't help but wonder what we will learn from the study of UY Scuti and similar stars. Despite its immense size and proximity to the end of its life cycle, we still have much to learn from UY Scuti's behavior. The variability in its brightness, its pulsations, and its mass provide valuable clues about how massive stars evolve and how they eventually meet their end. These stars are rare, and each one offers a unique opportunity to understand the forces that drive stellar evolution. In fact, UY Scuti and stars like it are crucial to our understanding of the larger structure of the universe. They give us insight into how galaxies evolve, how new stars form, and how the materials that make up planets and life are distributed throughout the cosmos. The explosion of a star like UY Scuti will not only provide us with valuable data about the mechanics of supernovae but also contribute to the cosmic cycle of star formation and destruction. As we continue to study these massive stars, we are also learning about the fundamental forces of nature. The forces of gravity, electromagnetism, and nuclear fusion all play key roles in the behavior of stars like UY Scuti. Understanding these forces and how they interact allows us to better understand the universe itself. In many ways, the study of stars like UY Scuti is a journey of self-discovery. By studying the cosmos, we are also studying the laws that govern our own existence. Furthermore, the study of UY Scuti and other red supergiants also opens up broader questions about the future of our own Sunday. Our star, while much smaller and less massive than UY Scuti, will eventually go through a similar process. It will expand into a red giant in about 5 billion years, though it won't reach the immense size of UY Scuti. Eventually, it will shed its outer layers and become a white dwarf, a dense remnant of the star's core. While our Sun won't end in a supernova like UY Scuti, it will still undergo dramatic changes that will have profound effects on the Earth and the rest of the solar system. By studying stars like UY Scuti, we gain valuable insights into the future of our own solar system and the fate of our Sun. UY Scuti is not just an awe-inspiring celestial object, it is a key to understanding the universe itself. From its massive size and pulsating behavior to its eventual death and the creation of new stars and planets, UY Scuti offers a unique perspective on the life cycle of stars and the processes that govern the cosmos. Its story is a testament to the interconnectedness of all things in the universe, from the creation of elements to the birth of new worlds. And as we continue to study UY Scuti and other stars like it, we are gaining a deeper understanding of the forces that shape the universe and our place within it. As we continue to probe the depths of UY Scuti's life and its eventual death, we find ourselves confronted with some of the most profound and mysterious questions in science. The sheer scale of its size and the extremities it reaches in terms of temperature, mass, and luminosity provide us with a testing ground for our current theories of stellar evolution, while also challenging us to develop new models to explain phenomena that we have yet to fully comprehend. The future of UY Scuti remains a topic of fascination, not only because of the dramatic spectacle it will present when it dies, but also because of the insights it could offer into the very nature of the universe. As we move deeper into the study of red supergiants, astronomers are exploring new ways to measure their properties with greater precision, trying to understand how such stars are formed, how they interact with their environments, and what happens to them in the final stages of their lives. In terms of stellar evolution, UY Scuti's life trajectory is both typical and unique. It follows a broad pattern that is shared by many other massive stars, but it also deviates in ways that make it a special case. The balance between gravity and the radiation pressure from nuclear fusion in its core has been delicately maintained for millions of years, but it is only a matter of time before this balance shifts, and the star begins to burn heavier elements. This will lead to increased instability in the star, causing it to pulse in size and brightness in a manner that we can observe from Earth. The idea that massive stars like UY Scuti are constantly changing in such dramatic ways gives us clues about the behavior of stars on the brink of death. As UY Scuti grows older and eventually explodes, it will leave behind a legacy that echoes throughout the cosmos. The material expelled in a supernova is not just a waste product, it is a critical part of the ongoing evolution of the universe. It will contribute to the formation of new stars, planets, and even potentially life, in a process known as cosmic recycling. This cycle of birth, death, and rebirth is one of the fundamental processes that drives the dynamics of galaxies, stellar populations, and the universe as a whole. Another aspect of UY Scuti that draws interest is its immense luminosity. As one of the brightest stars known to us, UY Scuti radiates energy that can outshine our Sun by a factor of tens of thousands. Its surface temperature, though cooler than that of more massive stars, still supports an energy output that is staggering. This luminosity contributes to the ways in which UY Scuti influences its surroundings. The intense radiation it emits pushes against the material surrounding it, creating strong stellar winds that blow off its outer layers. These winds, which can be extremely fast and carry vast amounts of mass, play a critical role in shaping the interstellar medium and enriching it with heavy elements. The mass loss that occurs through stellar winds is also important for understanding the evolution of massive stars. UY Scuti, like other red supergiants, loses a significant portion of its mass through this process. While this mass loss helps to stabilize the star in its later years, it also reduces the amount of material available for nuclear fusion in the core. As a result, the core becomes increasingly unstable, eventually leading to the star's collapse and subsequent explosion. The mass loss of stars like UY Scuti is a crucial factor in determining their ultimate fate, and astronomers are working to better quantify this phenomenon across different types of stars. Yet, perhaps one of the most profound aspects of UY Scuti's eventual death is the way it connects to the larger picture of cosmic evolution. Every supernova that occurs in the universe has far-reaching consequences. The shockwave created by such an explosion can trigger the formation of new stars, while the heavy elements it releases into space serve as the building blocks for future planetary systems. If UY Scuti's supernova occurs within a region rich in molecular clouds, dense regions of gas and dust, its explosion could ignite the formation of new stars, continuing the cycle of creation and destruction that has been playing out in our universe for billions of years. In this context, the death of UY Scuti is not the end of its story. Rather, it is the beginning of a new chapter in the ever-changing dynamics of the cosmos. The material that is ejected during the explosion will join the vast reservoirs of gas and dust scattered across the galaxy, eventually becoming part of new generations of stars and planets. The heavy elements produced in the supernova will be incorporated into these new systems, enriching the interstellar medium and furthering the cosmic cycle of creation. In this sense, every massive star that dies is a contributor to the ongoing story of the universe, leaving behind a legacy that stretches across billions of years. The energy released in a supernova is immense. When UY Scuti eventually explodes, it will release more energy in a single burst than the Sun will in its entire 10 billion-year lifetime. This event will not only be visible across great distances but will likely be detectable from Earth, providing astronomers with an opportunity to study the end of a massive star's life in real time. While supernovae have been observed in distant galaxies, the study of one in our own galaxy would offer unparalleled insights into the processes that govern stellar death. For all of the mystery that surrounds UY Scuti, one thing is certain: it has already made an indelible mark on our understanding of the universe. By studying this star, scientists can learn more about the fundamental processes that drive stellar evolution, the behavior of massive stars, and the ultimate fate of objects that seem almost beyond our comprehension. The story of UY Scuti is a reminder of the vastness and complexity of the cosmos and our small yet significant place within it. Moreover, UY Scuti serves as a powerful symbol of how far human knowledge has come in the field of astronomy. It wasn't long ago that we lacked the tools and technology to even detect stars like UY Scuti, let alone study them in such detail. With advancements in telescopes, data analysis, and our understanding of astrophysics, we are now able to peer deeper into the universe than ever before. And as we continue to refine our methods and extend the reach of our instruments, we will uncover even more secrets about UY Scuti and other stars like it, furthering our understanding of the very fabric of the universe itself. As we gaze up at the night sky and imagine the distant future, UY Scuti stands as a testament to the wonders of the cosmos. Its existence challenges our sense of scale and forces us to confront the vastness of space. It reminds us that we are part of something much larger, something ancient and ongoing. And in the end, the story of UY Scuti is not just about one star. It is about the infinite dance of creation and destruction that defines the universe, a dance that will continue long after UY Scuti has burned its last. The final death throes of a star like UY Scuti might seem like a distant and almost insignificant event in the grand scheme of the universe. However, it is precisely through these cosmic events that the universe evolves and grows, perpetuating the cycle of star birth and death that has been ongoing since the beginning of time. The energy and matter released in the supernova explosion of UY Scuti will, one day, become the raw materials for future generations of stars, planets, and perhaps even life itself. And so, the end of UY Scuti's life is merely the next step in the ever-continuing story of the universe, a story written in the stars and told across vast expanses of space and time. In the aftermath of UY Scuti's eventual demise, the galaxy will witness a series of transformations that will be felt across vast distances. For a brief moment, the star will shine brighter than anything else in its region, a beacon of light that signals the immense energy at play. As the star explodes in a supernova, it will release not just light but a torrent of particles, radiation, and energy that will reshape the very fabric of the surrounding space. These powerful forces will alter the dynamics of the nearby interstellar medium, pushing the gas and dust outward in a shockwave that can travel millions of kilometers per hour. This shockwave will compress surrounding gas clouds, triggering new cycles of star formation, and infusing the local environment with heavy elements that were once forged deep within the heart of UY Scuti. The impact of such an event cannot be overstated. As these elements spread out into the cosmos, they will become part of the next generation of stars and planetary systems. It's a fundamental part of how galaxies evolve over time. The elements produced by UY Scuti in its supernova, elements like carbon, oxygen, iron, and others, are essential for the creation of planets, and even life, as we know it. In this way, the death of a star is not a simple ending, but rather a vital process that fuels the cycle of creation throughout the universe. One fascinating aspect of UY Scuti's supernova will be its potential to influence its stellar neighbors. In the process of exploding, UY Scuti's shockwaves may impact nearby stars, triggering the formation of new ones or possibly disturbing the orbits of other stars in its vicinity. Such events are rare, but they serve to underscore the interconnectedness of stars within a galaxy. No star is truly isolated, Each one plays a role in the broader cosmic tapestry. Furthermore, the study of UY Scuti's eventual death provides valuable insight into the larger process of stellar evolution. Understanding the mechanics behind the supernova of a red supergiant like UY Scuti helps astronomers refine their models of how stars evolve and die, especially when it comes to the most massive stars. By observing stars at different stages of their life cycles, scientists can better predict the future of our own Sun, which, though much smaller than UY Scuti, will go through its own stages of transformation and eventual death, albeit in a different manner. The death of UY Scuti will also provide a unique opportunity to study the behavior of supernova remnants. These remnants are the materials left behind after the explosion, vast clouds of gas and dust that expand outward from the point of the explosion. In some cases, these remnants can form nebulae or even collapse under their own gravity to form black holes or neutron stars. By studying how UY Scuti's remnants evolve, scientists can gain deeper insights into the processes that shape the evolution of the universe at large. Each supernova provides a snapshot of the universe's history, revealing information about the conditions and events that led to the formation of not only the star itself but also the galaxy and larger cosmic structures. Another area where UY Scuti's death could have profound implications is the study of gravitational waves. These ripples in space-time, which are produced by extremely violent and energetic processes like the collapse of a massive star into a supernova or the merger of two neutron stars, have been detected by scientists in recent years. Gravitational waves carry information about the dynamics of such events, and the explosion of UY Scuti, given its size and energy, could potentially generate detectable gravitational waves. If scientists are able to capture these waves, it will offer an unprecedented glimpse into the violent processes occurring during a star's death. The study of these waves could eventually lead to new discoveries about the fundamental nature of gravity and space-time itself. In addition to the scientific implications, the death of UY Scuti offers a deeper philosophical reflection on the nature of life, death, and time. The star's life cycle reminds us that all things, no matter how large or small, have their beginning and their end. UY Scuti's immense size and energy might make it seem eternal, but in reality, it is a transient phenomenon, just like all stars in the universe. Its explosive death will serve as a reminder of the fragility of existence and the inevitability of change. As a species, we are constantly confronted with the forces of nature that shape our own lives, and in many ways, stars like UY Scuti are a reflection of that larger cosmic truth, that everything in the universe is in a constant state of flux. Moreover, UY Scuti's death will serve as a cosmic marker for the future. It will be a moment when the universe reflects upon the cycles of creation and destruction that have played out for billions of years. In a sense, the end of UY Scuti marks the conclusion of one chapter and the opening of another. Even though the explosion will be incredibly far from Earth, its effects will be felt in the scientific community, driving new research and discoveries that push the boundaries of what we know about the cosmos. As we peer into the universe, the massive stars like UY Scuti remind us of the mysteries that remain to be uncovered. While we may never be able to witness the death of this particular star in real time, our continued study of UY Scuti, along with other supergiants, offers invaluable insights into the fundamental processes that govern the universe. The questions we ask today about stars like UY Scuti will shape the discoveries of tomorrow, guiding our journey through the vast expanse of space. In the grand scale of the universe, UY Scuti is but one star among billions. Yet, it serves as a symbol of the wonders that await those willing to look beyond the familiar and the known. It challenges our perceptions of space, time, and the forces that shape the cosmos. Through the study of such stars, we come to understand not only the nature of the universe but also our own place within it. Ultimately, the story of UY Scuti is a story of the cosmos itself, of the birth, life, death, and rebirth of stars. It serves as a reminder that we are part of something much larger than ourselves, a part of a vast, ever-evolving universe that continues to surprise and inspire us. The death of UY Scuti will not be the end, but a new beginning, a new chapter in the endless cycle of cosmic creation and destruction. As we look up at the stars, we are reminded that the universe is alive, constantly shifting and changing, and that every moment brings with it the possibility of discovery. And in that discovery, we find not only answers to our questions but new questions that lead us further into the unknown. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.